All right. So in wiring diagrams, it gets to be a little abnormal because, let's say you're doing diagnosis based on a code, like a diagnostic trouble code. You would get some sort of like steps, some sort of steps. Like step one, check the battery voltage. Step two, check the voltage at the sensor that's related to the DTC. But when we cover wiring diagrams, we're just going to overall back up and take a look at the diagram, and you're not going to get a whole lot of context. So you need to be able to look at this diagram and interpret it, but you don't necessarily need to worry about the whole diagram. You really only need to worry about the parts of the diagram that could cause the potential fault, right? So let's give an example. If a car came in with one headlight not working, you would get a wiring diagram for both headlights and probably some other stuff and probably a bunch of stuff. Then a lot of times what you do is look at it and do a basic tracing. And if you trace it, then you should know what voltage to expect at different test points. But you don't need to trace the whole thing because nobody collects your work at the end of the day and says like, oh, did you trace everything? Right? So we're going to go through and trace a lot of these wires so you know how to trace them. And then after, we're going to do some specific diagnosis. So I'll give you like some examples, and then we'll get our own diagrams randomly and talk about what we would trace and what we wouldn't bother to trace. All right, so it's a little bit unique, but we'll jump right into it. So it's wiring diagrams and tracing the current. Okay, I call it wiring diagrams, but when I first started my career, I called it schematics. It'd be like, pull the schematic up. Give me the schematic. And you can say it either way. I just say wiring diagram now. So wiring diagram, schematic, same. Schematic's kind of vague. So if you want to be a little bit more specific, you do like an electrical schematic, right? Because a schematic could mean a number of different things, not necessarily just electrical. And then basically, it's a map of all the electrical components. So let's say you don't want to work on cars, you want to work on apartment buildings. Somewhere, there's going to be a whole schematic of the electrical system of that apartment building. It's going to show where the main breaker panel is. If there's sub-panels, it's going to show where the wires go, where they end. A lot of times, it'll show what the wire size is, right? So this is not only unique to automotive, but what we're going to cover is going to be really specific to automotive. If you have a problem in the electrical system, it's not a good idea to just randomly go poking around trying to find it. You could spend years probably trying to find it. So you need to be able to look at these and read them fairly quickly. Cool. So when you see these wiring diagrams, they're going to have some different symbols. So let's see if you remember some of these. We'll even highlight them so that you can follow really well. Let's say that we're looking at this one. That's one version of the battery. And not every wiring diagram will have the battery on there. So like a typical, let's say that you're using some sort of aftermarket service information. A typical wiring diagram is going to be so big, you can't fit it onto one page. So if you're in all data and you're like, let me look at the headlight diagram, you might have one diagram showing the battery, and then you might have like a wire coming off of that and going over here. And then on the next page, it may no longer show the battery. And it may say like it might have a letter here, and it might say like C from A. Ultimately, on every diagram, you can always trace the positive back to the battery. Maybe not on the page you're looking at, but if you were to put pages together and look, and even sometimes you got to get into the power distribution diagram or something, you can trace it back to the battery. Makes sense? And then similarly with the ground, if you really think about it, the ground always goes back to the battery too. But on the diagram, it may not show that. So typically on the diagram, it would show, something like this, just showing ground. That would indicate that it's going to the chassis. Remember that? We talked about that a little bit. So if a thing goes to the chassis, that means eventually the chassis makes it all the way back to the negative terminal. Cool. So keep that in mind as we proceed. Then let's say we could pick each one of these, and we've kind of covered them, but this is a little bit of review. You got your fuse, that's typical. You got fusible links or circuit breakers, and they're not necessarily going to be labeled on your diagram. So if it's a fuse, I think everybody's familiar with that symbol by now, but if it's a fusible link, you see it looks a little different. And if it's a circuit breaker, it looks even a little bit different. And that'd be pretty important to know. Let's say you have to go back and you have to test in the fuse box. You need to know if you're looking for a fusible link, a circuit breaker, or a regular fuse. And then with bulbs, they can vary a little bit in design, but overall, this is your typical bulb. Have you guys ever seen dual filament bulbs? That would be pretty common for like a tail light, stop light. So the tail light might be this one, and that would glow kind of dim. But then if you apply the brakes, the more bright stop lamp filament will glow, and that'll make them brighter. So if you come up on a car and you see that the red lights are on behind it, you're kind of like, are those brake lights or tail lights? And then if they step on the brakes, they get a lot brighter. That's how they do that. Those are one bulb with two different filaments, which means we're going to probably have like one wire for the brake, and then maybe a different wire for the regular tail lights, and then this would be the ground, right? So it's one bulb that can glow two different ways. It'll most likely have three wires. It's also common for turn signals, right? You may have a tail light that also functions as a turn signal. And then sometimes on a lot of newer stuff, they've made the turn signal now amber, but you know, in some cars it's a brighter red. Cool capacitor, not a real big deal. Now, when we look at these, this is going to be very important to understand as we proceed. Let's look at these. Can you tell that those wires are spliced? You notice there's a little dot right there. If wires cross each other and they don't seem to really connect, they don't. They just don't have enough room on the paper to not have the wires cross each other. So eventually they got to cross over. But if they come together with a dot, that means those wires are spliced. So they've been joined together. Electrically, they're the same. This is basically, if you look at this is basically a fork in the road right here. So electrically, those wires are connected. Although physically, they might not look like this. Like when they're connected, they don't necessarily come together at a nice right angle, like an intersection. They may very well come down like this and kind of like go along with each other and then be joined at the bottom. And they might look a little bit weird, but how we test it, you just have to know that those are actually electrically connected. Cool. So you could join a number of different wires together like that. And then you've got a single pole switch. So this one you can tell is normally open. That's kind of typical. If it's drawn closed, that would be a normally closed switch. We do have both types, if you recall. Then we got, this is more like a thermistor actually. And this would be a variable resistor. So we could have different, those would be typically on sensors. And we could get a little bit into sensors. And then here we got an ignition coil. We got several different grounds. A couple of these are really critical for you to know. If you look, this is a chassis ground, right? That one we talked about. What the heck is this thing? The ground doesn't have a wire on it. So you're sort of like, what is that? Well, that means that component itself is grounded, like the housing is grounded. A good example would be the starter. If you ever notice on a starter motor, we don't have a ground wire going to it. We don't need a ground wire going to it because the whole body of the starter is actually bolted to the block, right? So the ground comes from the starter itself, where it bolts to the block. Or an alternator is the same, or a lot of times a horn. If you go to look at a horn, the horn will a lot of times show this what they call like a component ground like this. That's because the horn is bolted to a bracket and the bracket is bolted to like a radiator support or something. It's grounded through itself. Kind of makes sense? Now what's crazy about that is it makes you think you don't have to check it. And I'm going to say like 99.7% of the time, you pretty much don't. But I've seen a few examples where, let's say, you got some really cool old hot rod and you decide you want to like totally resto mod it, and you take it apart and you have all the parts powder coated and everything's all powder coated really nice. And then you bolt your starter up to like your recently powder coated engine block. See where I'm going with this? You no longer have a good ground contact because it's no longer metal to metal. Now you have your nice bare metal starter bolted to a powder coated block. You may not have a good ground right there. So there is a way to actually test the component ground, and you test it very similar to a chassis ground, but rather than testing the wire, you actually just put your lead right on the component itself and see, is that got a good ground? So if it's a good ground, it should have 0 volts. The way I would test it is I put my red lead on the positive battery terminal or a known good 12 volts, and then I take my black lead and I just touch the housing of the thing, the starter. And if I read 12 volts on my meter, that shows me that there's a good ground there, right? Because my red is on a known good positive. So if my black lead is on a good ground, it would read 12 volts. That's a good way to test it. But not real common. And then if you notice, this is an internal ECU ground. So sometimes what we do with control modules is we will have a ground inside the control module that we will send out to sensors, for example. So this would be like a sensor ground. If you wanted to provide a ground for your throttle position sensor, we don't necessarily take the ground terminal and run it to chassis. There can be a lot of feedback and current flow. There's a lot of stuff happening in that chassis ground. So we may run it all the way back to the ECU and have the ECU provide a nice, clean, very consistent ground. So that's another type of ground. You test it really the same, but just know it doesn't necessarily go to the chassis. It may go all the way to the ECU, which, if you think about it, gets its ground from the chassis. So it's kind of similar, right? And then if we look at breakers, aren't real common. Different types of motors, right? That would usually have an M. Piezoelectric sensors are not super common, but like with a knock sensor, it has a certain look. Now connectors right here, there's actually more to that than you'd think. You'd be like, oh, there's a connector there. So if you look, say we drew one. A lot of times we'll call that the chevron. Now without making this a health class, you should be able to imagine that this is the male and this is the female down here, right? So we'll make an M and an F. But what we're typically talking about there is the actual terminal. So when you look into connectors, let's say that you have a connector and it's like this, and there's 2 little terminals inside. This part here is all plastic, right? All this stuff is plastic. Inside here, this is a little metal terminal, this is a little metal terminal. When you see the wiring diagram, they're talking about, in every case I can think of, they're talking about the terminals, right? So if you looked at your connector and you had a little male pin like this and a little female pin like this is letting you know that side is male. So for whatever reason, if you decided, hey, I want to test this wiring diagram, and you're like, let me check the male side, you'd actually find the connector and see on the wiring diagram, everything flows top to bottom normally. But in the car, it might be going this way, it might be going that way, it might be going this way. So you may find this connector and be like, well, which side is coming from the battery? And you're like, I don't really know. Well, on the diagram, if it shows the arrow and this is coming from the battery, you'd know to go to the male side. You disconnect the connector and you'd actually go to the male terminal. Or if you wanted to test, let's say this goes to the load down here. If you want to test the load side, that would mean you go to the female terminal right there. Cool. Now maybe there's some exception where that male-female chevron is talking about the plastic connector, but I haven't seen that. I've seen where it talks about the actual pin. So it's kind of funny, but a lot of times the male pins are set inside of a female plastic connector, and the female terminals are set inside of the male part of the connector. So when you slide the connectors apart and it's plastic on plastic, we're not worried about the status of the plastic. We're worried about the terminals. Kind of get what I'm saying? All right, trust me, you'll see. We'll be looking at that stuff. Cool. Different types of switches. Relays you're definitely going to see. Do you recall on a relay, remember this coil part right here? Remember that coil part, that is a load. Remember this going forward. The coil part is a load. So if you saw the coil like this of a relay, and then over here, we have the switch part. If that was the load, just keep in mind as we do this, we should have 12 volts coming down. And what should we have after the load if it's working? It should be ground down here. Right, so just remember that part is an actual load. However, over here, this should not have, like, let's say 12 volts coming in, ground going out, unless it's open. If it's closed, this is just a control device. It's not actually a load, right? So the relays are kind of weird because they're both a load and a control device. And when we get into our first diagrams, you'll see the first thing we want to do is identify all the loads in the circuit. Then you got a couple diode types. We don't have to really stress about the difference between a diode and a Zener diode, but that was in components earlier. And then here saying this connector is attached to a component. So that means the connector is on the component. Another example we could pick would be the horn. If you go to the horn actually has a connector that plugs directly into the horn. So that's what the connector's right there. And here's another type of switch. This type of switch could seem confusing because if you notice right now we're in off, right? Well, can you think of your blower motor? When you jump in the car, you turn your AC on, or your heat in the unlikely event here. You can turn it to off, right? That's where this is right now. What if you turn it to speed number 1? That's when it's like this. What about speed number 2? That's when it's like this, right? So the reason that can be kind of confusing is when you go to test the circuit, it depends on the position of the switch, right? So like if you had a blower motor that didn't work on speed number 2, I would just go ahead and trace that circuit as if the switch is on speed number 2, and then I'd put the switch on speed number 2, and I would draw it out like that. Whereas if you trace it with it in the off position, that's only going to tell you what should have if it's turned off. And if your problem's occurring when it's in the speed 2 position, you might as well draw it as if it's in the speed 2, trace it, and then do the test while it's in speed 2. Does that make sense? Like, so to reword that, if the customer states the horn doesn't work, you probably need to test it with the horn button pressed, right? Like if you don't press the horn button, you're not testing anything. You gotta push it. Or if it was the headlights and you want to test the headlights, it'd be pretty logical. You turn the headlight switch to the on position and then you do your testing. Does that make sense? So the wiring diagram, there's not, let's see how many speeds we got. We got off, 1, 2, and 3. There's not going to be 4 versions of the wiring diagram. You're going to get one diagram and it's probably going to be drawn in the off position. And then if you know that it's got a problem in speed 2, you're just going to yourself just be like, no, it's in speed 2, and then trace it in speed 2, and then test it as if you're in speed 2 with the switch in speed 2. Cool. Okay, another type of relay, not a big deal. LEDs, remember the LED is the load. And if the LED gets 12 volts in ground, it will light up. That's mostly what we use them for. Photodiode, slightly different. It's a diode, but the diode will allow more or less current flow depending on the amount of light coming in. If you notice, the arrows are going in like this on the photodiode, but on the LED, they're going out. The LED makes light. The photodiode detects light and changes current flow accordingly. Now look at this connector. This one is very different when compared to that one. This one is saying there's a connector, but it's not right on the component. It's on a pigtail. You guys ever heard of the term pigtail? Now, it may be surprising, but at one point I had enough hair to have pigtails. But that was a long time ago and not the case anymore. Pigtail would be like, let's say you have a wheel speed sensor. This is very common on wheel speed sensors. There's the sensor, but there's no connector at the sensor. The sensor has a set of wires that are attached to it permanently. And they go like somewhere out here, like this, like out here. And then they have a connector, right? So a pigtail would mean like it's a little short whip coming off of the component and the connector is a little separate. It's fairly common. It just means if you want to test the component, you can't test it here. You got to test it up here at the connector after the pigtail. Then there's a couple of different types of switches and some solenoids, which, you know, solenoid is very similar to a relay. This part right here would be the load. And if this gets 12 volts in ground, it will make some sort of movement. The solenoid will go up or the solenoid will go down, and fluid will flow or fluid will not flow, or the door locks will unlock or the door locks will lock, right? So just that's another type of a load. Not real tough. Okay. So that should get us a little bit started so we can get into how we're going to do this. If we look at this diagram, right, and we won't go super crazy on this, but let's just look at the components more so than do the full trace, because we are going to trace some stuff, but we're a little premature. Can anyone find, well, you tell me, give me one component that you see. All right, we got some good stuff coming in. So let's go with fuse, battery, several other fuses. What else can we see? Ah, we got a relay, huh? We see one relay. We see another relay. All right, so we got bulbs. So let's do bulbs like in maybe this color. These are all bulbs. All right. Ah, so we also have some switches. Okay. All right, so we got a switch here and a switch here. Now you notice technically there's a switch here too, right? And that's where the relay is kind of frustrating, because the relay is a switch, but it's also a load. So it's kind of both, but that's all right. We can get it. What else do you see? Oh yeah, there's definitely some grounds. Yep, okay, makes sense. What else? Oh, there's another ground, sneaky ground down there. How about, what's this here? There's a splice right there. Okay, and some other cool details on this is, look, we got some terminal. We got the connector information here showing you which is male, which is female. So if you can't see, it's coming off like this. Right, so if we wanted to test the wire coming down, we would actually need to test at the female point, if you see that. If we were to test at the male point, that's really what's going into the lamp itself, right? So just kind of breaking that down, that's how it would work. And then there's another detail on here. You see these? It says 2. It's too much information to have on one page. So normally what you need to do is, if this is page, we'll go with 3 of 5, you'd probably need to look at either 2 or 3, and then you'll see on the other one there will be like an arrow like this, and it'll say 2, and you can continue to see where that goes or where it came from or whatever. Go ahead.
Okay, looking at this diagram,
Mm-hmm.
what would make me think to check 2? What situation or problem?
That's a good point. I'll break this down. We're going to spend a little bit of time on this diagram, so we got plenty of time on this. So if I were to look at 2, let's just do a basic trace on here. I'm gonna trace it in red, but I actually this is kind of what I'm getting at is it probably is gonna be red because look, it came from the fuse. So if that goes over to here, if I was looking at that and it came from here, it looks to me like that's gonna be either one of a couple things. It could be, I think that's going to have to do with the tail light. But if you notice how this bulb is small, I think that's actually going to be more like parking lights. So in the back, when you turn the parking lights on, let's say you jump in and you turn the switch to the very first little click. You ever notice how it doesn't make the headlights come on? It makes like your tail lights come on and your interior lights come on. You ever notice some lights in the front come on too? But not the headlights, huh? I bet you that number 2 is going to probably go to the parking lamps. So let's say that we have a vehicle and these bulbs are out and the parking lamps are out. It's just letting you know that's all the same circuit. And so you might not necessarily need to go chase 2, but you'd be like, oh, that goes up there and does something. Then you could look at 2 and be like, oh, this goes to the parking lamps. Hey, you know what? That makes sense. The parking lamps are out and the little lights and the tail lights are out. So if all those are out, see if you follow what I'm saying. If all those are out, do you think it's a problem right here? Because if the wire is broken right there, what would be affected? Just that one. But see, if I knew that 2 went out to the park lamps and those weren't working, I know the problem's not going to be back here. If I look at this, right, and I were to trace this in a little bit smaller drawing, there's a splice here, there's a splice here. Wait a minute, what if that fuse was blown? What would that cause? It would, look at it though, this fuse feeds the back and the front. So it would cause them all to be out, right? So sometimes you might want to know where that wire continues to go to give you a clue. So if I were diagnosing this car and it had no rear park lights and no front park lights, I know it's not going to be here or here or here. I know it's got to be somewhere before it splits off. So I'd be interested in checking anywhere between, let's say, let's do a color change because it's getting a little ugly. I'd be interested in checking anywhere between like right there and if we were to trace it right here, but technically it even goes, it looks like it comes from there ultimately. I'd be interested in anywhere from here all the way through and down to here. An open in the green part of the circuit would cause the whole red part of the circuit not to work. Kind of makes sense, sort of, a little bit. Don't worry, we'll get a little more and more into it. So this is your first real wiring diagram that we've gone over. And let's say I go a little bit further into this. In fact, I'm looking at this. Some of these are going to have to be stop lamps. But I don't know that I have the information enough. That's when we might have to change over to a different page. So let's just say, let's start with an activity of what I like to do is let's identify the loads. What do you think I mean by, let's pick every load in this whole system. You know what I mean by that? What are the load? What are the things that do work? The load is the thing that consumes the voltage and does work as a result. Which ones? Give me one. Come on. Yeah, here's 1, 2, 3, 4, 5, 6. Those are all going to do work for us. Yeah, so those should be the things that consume the voltage. I agree. But there is more. Those are the things that consume voltage in exchange for making light, right? If it was a motor, those would consume voltage in exchange for making movement. But there's another type of load right here that it consumes voltage in exchange for making magnetism, which is kind of similar. Yeah, so this is also a load. This is also a load. I agree. All right, so everybody 100% needs to be able to identify the loads in the circuit every time. If you can't identify the loads in the circuit, you got no chance of doing this at all. Okay, and that is everything. Those are all the loads. Now, let's say I want to identify the control devices. You know what I mean by that? Control devices would be like switches and sometimes control modules that turn lights on and off. Where are the control devices? In other words, how do you control these lights? Yeah, that's correct. Yeah, you don't overthink it. That's it. This one, and then technically this side of the relay is correct, and this side of the relay is correct. Now, once you have that and you understand where the loads are, then probably the way that I'd proceed on this, once I really understand how the circuit works, right? Sometimes I got to study it a little bit. We can do this several different ways. But the way that I would normally proceed is I would go ahead and I would look at the load and say, like, coming into the load should be red. Going out of the load should be green because it goes to ground. So actually, this one is just a little bit more confusing, but let's just say RG. You know, this didn't exactly show it. So if I were to make it maybe a little bit more simple, I would say if these are the loads, right, I know that I'm going to probably have reds coming in. And then if you look, we're going to have a green go into the ground. And if we understand that, then we should say most likely we should have probably a red coming all the way to this point. Let's trace it back and see if that makes sense. Let me pick, how about this one? No, that one's a little, this one's a little tricky. I'll give you that. Let's go with, yeah, the other way. In this case, actually, I may switch and I may draw just how the current flows, because this one's kind of a weird diagram. What if I pulled off the battery? We agree that it does this, right? And then you saw that that was a splice right there, if you could see that. So if that's a splice, this is definitely going to go down. And it goes here, here, and here. Then if you kind of look at that, the red in a way would stop at the load right there. That's the coil, right? So then I'd have to switch over to hopefully ground. The problem is, you know, right now why this wouldn't be good ground? Can you guys see what the problem is here? The light switch is open because ground's right here, but the ground's not making it through the light switch yet. So we need to turn the light switch on to do this test. When you turn the light switch on, this switch should drop down and make a connection. And then, yes, we would get ground all the way through. If we get 12 volts here and ground here, what's that going to cause this coil to do? Think you recall? Magnetism, which is going to close the relay, which then means red will go like this, go through the fuse. Should it drop anything through the fuse? Not really. It should still be 12 volts-ish. Go to here, go to here, go to here, go to there. But it also goes out this way, like we were saying before. It also goes down. Right. So if you had a problem with that whatever those rear parking lamps, this is pretty much what you would do. You would trace it just like this. And then the thing is, once you end up with your trace diagram, the customer doesn't ask for that. They don't want to see that. They don't know how to read it. They don't really care. The only reason that you trace this diagram is so that you understand how it works and you know what your voltage reading should be. So guess what? Anywhere that's red should be about what voltage? Oh, I forgot to plug in my charger. Anywhere that's red, what do you think? Yeah, that's correct. A good source voltage would be a good reading for the red. What about for the green? Bingo. And now once you have this traced, you're ready to start figuring out what you should test. And when you do test it, you pretty much know what your reading should be. Now, maybe not exact, but about 12-ish and about 0-ish would get. So if I wanted to test, let's say, this point right here, that should be 12-ish. If I wanted to test this point right here, that should be 12-ish. If I wanted to test all the way down here at this point, that should be 12. But what if I wanted to test right here? That should be 0, right? So the wiring diagrams are mostly a guide for you so that you know what the reading should be when you're testing all this stuff. All right. So that's how we traced it, and that one was honestly not a great one to start with. So don't worry, we're going to get some much more basic diagrams here. All right, and then remember it's got symbols to represent different components, and it's got the lines that represent the wires. So you guys all caught that, right? These lines are all little wires, right? And you could see the components. Now, what this doesn't do is tell you where anything is. So if you're looking for this fuse, it doesn't necessarily mean it's 1 inch from the battery. It just means electrically that's how it's laid out. So if you want to look physically for that fuse, well, that's a different thing. That's not really tracing wire diagrams. And I actually pulled it up on another screen so I could show you, like, there is a way. That's component view. That's component location. So if you want to do component location, that's not a wiring diagram. The wiring diagram just shows you electrically how it's laid out, not physically. Okay. And then if you had the whole, just imagine this wiring diagram was fairly complex. Imagine if you had one wiring diagram for the whole entire vehicle and every wire on the car and every sensor and every light and every switch and everything. It'd be ridiculous. So we don't do it like that. If you want to look up how the headlights, something about the headlights, you look up the headlight wiring diagram. You don't look up the whole entire car wiring diagram, and you'd have to roll it out across the whole shop and walk over to stuff and follow it around. It'd be way too complex. Cool. So it's more like system and subsystem. So if you're looking into a headlight problem, you look in the headlight wiring diagram. There may even be several for just the headlights, but that's okay. And they have a lot of information. So right here, these are pretty good. Some of the wiring diagrams you're going to notice will have even more information. They'll actually have little terminal numbers. One thing I did forget to mention was if you look right here, this says G. This says BW. This says LG. What do you think those mean? W. WB. Those are colors. So what do you think W is? Definitely. What do you think LG is? Light green is correct. BW? Two colors. It's going to be black and white. Blue is usually BL. So if it's BW, that's usually a black wire with a white tracer, a white stripe on it, because there's so many wires, they need to start doing multiple colors on the wires. Light green, red, yellow, red, black, red, green, green, white with black. White with black is different than black with white, right? It's primarily black with a white stripe, whereas this one is primarily white with a black stripe. Cool. So that's going to be very critical in you locating the correct wire. But as we get further in, you'll see we also use terminal numbers, and you can track it down to where it's located in the terminal, in the connector. Cool.
Any question about
Go ahead.
the colors? L is always light.
Well, I wish. It's kind of like, it'd be nice if there were standards that everyone followed, but unfortunately, you may see just an L, and you'd be like, "What is that?" And I've heard it called lavender, or just light blue. So, not always. But if it says LG, I have never seen that be light gray, but I've seen it be light green, so I'm pretty confident it's gonna be light green. Yeah, but if you ever see just an L standalone, Japanese for some reason like L, and I I think it's lavender.
So
But
G's not always green, it's also gray.
no, I've only ever seen gray GY. Yeah, but I've also seen green GN. So it's sort of like you go in with mostly an understanding, and you just leave a little bit of room for one manufacturer to do something different and one to do something different, but probably pretty consistent. The good news is I'll show you. You don't necessarily go only by wire color. You should be able to go by the terminal number. So if it says it's in terminal number 1, and you look in terminal number 1 and it said it was going to be an LG, and you look at it and you're like, that's not light green, that's like light gray, then you'd be like, all right, well, apparently it means light gray because it's definitely in the terminal number 1. So there's little couple tricks we can do to make sure we're on the right wire. If you're on the wrong wire, you are going to misdiagnose that. Let you know for sure. Cool. And you'll see, we'll look at a few different manufacturer diagram just to show they can do stuff a little different. Sometimes even the symbols can be a little different, which is great. Cool. So we were pretty good on the splices. We talked a bit about that. Now, sometimes on the wiring diagram, it'll look like this. If you have a wire like this and this other wire, let's do it in color because some of the new diagrams are full color. They're pretty cool. You have a wire coming over like this. If they're different colors, it's a good chance they're not going to be spliced. Sometimes it'll do this little hop over thing, whoop, like that. It goes whoop. If you listen really carefully, you can hear what's the noise that Nintendo makes when Mario jumps? That's what it does. If you listen really carefully, you're like whoop. It helps. It does help. Those are definitely not connected. This would be confusing to me because it's like, is it connected? Is it not connected? I'd say generally this is going to be a no. But if there were two different colors and it came together with an intentional something, then those are definitely connected. The good news is it makes more sense if you have a green wire, let's say it's ground, and they bring another wire over, they're probably going to have that wire be the same color because they're both ground, right? So it'd be a little abnormal to have different wire colors come together and be spliced, but it's not unheard of. Like a good example would be if the vehicle's using white with black stripe as ground and a bunch of them spliced together, you'll see a whole bunch of white with black come together and you'd be like, oh, that must be a splice. They're all just like bundled up in a thing and taped or put in some sort of heat shrink. You'd be like, oh yeah, there's the splice right there. And this splice can be labeled like S7 would be splice number 7. In the case that you thought it was a problem with splice number 7, you would be able to look on component locator for splice number 7. See, if it's just a splice like this, it has no name, like I don't know where to find that. So we typically label it with a name or a number or something so you can locate it. Cool. Here's splice S101, S102, S103. But these, however, see how these have a dot? So if you see dots on the screen, that means that's a splice. But if you see where wires just cross each other, they didn't forget to put the dot thing. That means those are not connected. Kind of makes sense. So it can vary a little bit. And this is breaking down that original diagram that you would have seen. All right, and then let's say that we were looking at those wire colors like we talked about earlier before. Um, BL is blue in this one. Interesting. BK being black, that makes sense. Brown. I don't know. I got to be honest with you. I have never seen DR as dark blue, but apparently it's out there somewhere because that's the example. Dark green, gray, light blue, light green, orange, pink, red. I don't usually see RD. I usually just see R. Tan, I guess. Violet. WT, I usually just see as W. YL, I usually just see as Y. Right? So it could be a little different from one manufacturer to the next. And then what's really cool is on some of the nicer diagrams, they'll actually be in color. And the color is pretty cool, but also it could be a little overwhelming. Sometimes a little hard. If it's a complex diagram, it's all in color. It's like, whoa, it just looks like somebody had crayons and just like they had them all in their pocket and they fell on them. There's just colors and stuff everywhere, just a mess, like confetti. It looks like confetti. Mm-hmm. Oh, let me pick that back up. This one's nice because it really spells it out. That'd be another cool thing. But you notice in this picture, we brought in something new. What is that? Why is that there? Give you a clue? That's the terminal number, right? So what's pretty cool is if this has a connector, this may even tell you the name of the name of the connector is S3. So it's connector S3. Connector S3, we could look up and we could get connector N view, and it'd look like this. Maybe 1 and 2. So if you're like, oh, 1 is supposed to be on the left, and then you could double check it by this one should be white and black. And then what should terminal number 2 be in color, just to make sure you're on the right connector and everything? What should terminal 2 be? Red. Yeah, exactly. So see, when you've got the terminal numbers and the colors, it just helps to make sure you're not going to be confused. Then if you were to look down here, let's look at JC as a junction connector. Connector S16, I know that may have like a whole bunch of wires. So maybe like 1, 2, 3, 4, 5, and 6. And you'd be like, oh, 1 is red, and 2 is red, and 3 is red, and 4 is red, and 5 is red, and 6 is red. Sometimes we'd have all those same wire colors come into a connector because it might be like a splice bar, a splice comb. They'll have a bunch of stuff coming together, and it'll connect into something, and that something will just be like a piece of metal that basically makes them all one circuit. You know, that's kind of common too, which is that was a giveaway by JC. It's a junction. It's a junction connector. It's a junction where things are coming together. Right. So if we were to look at just this most basic diagram we have here, can you tell what this load is right here? It's labeled. What would you say if someone got all up in your face? Back up. What do you mean back up? It's the reverse lamps. You put the car in reverse, the little white lights come on in the back. You're walking down the aisle in Costco where everybody's parking and going crazy. You know if a car has the little white lights lit up on the tailgate or on the trunk or whatever, don't go behind that one. That's how you know that they're in reverse. So if this is the backup lamp and we were to look at this, what do you think? You don't have the whole diagram right here, but you know that this load needs a 12 volts and it needs a ground. Which one do you think is which? Well, if it were me, I'd say probably the red is the 12 volts, wouldn't you? What do you think the white and black's going to be? That's probably going to be the ground. So if that backup lamp didn't light up, you could see pretty quickly like, oh, well, I can test that. What should the voltage be on terminal number 2? There's terminal number 2 right there. It's red, so what should it be? Yeah, exactly. Boom, just like that. Which means, what should be on terminal 1? Well, that's on the green side, so that would be ground, right? So what you guys learned on the boards, you can see really easily. But when you roll up to the car, you can't really tell which one the positive is and which one the negative is. It's nice if it's red and white and black, but if there were 2 wire colors, red and yellow, which one's the positive, which one's the negative? I don't know. We got to look it up on the diagram, right? We get into that when we do on the car, but there'd be a connector. I can draw something. It'll be a little ugly, but there'll be this plastic connector, right, with the 1 and the 2. And you would put your lead, we'd use a little back probe terminal, and we'd slip a back probe right in here. Slip it right in there and just barely touch the terminal. And boom, there's your test point. So don't worry, we're going to do that. That's a little separate. That's on back probing. And we can cover it a bit right now, and then a bit more with wire and terminal and connector repair. And then when we get into the unit for lighting systems, you're going to be back probing. So if you understand the diagram, you need one little bit of help where we do the back probe, which just slides right into the terminal. And then you can be like, oh yeah, it's got ground, or it doesn't have ground, or it's got what it needs, or it doesn't have what it needs. And that's how you do your diagnosis. Remember, you guys told me you want to be able to bill out big bucks, right? Diagnosis bills. I mean, you charge legitimate money for that, but you don't guess and then take the customer's money to guess. Nobody really was going to pay you to just guess. Okay. Uh-huh.
Like when you say the S16, for instance.
Yeah.
And the diagram says S16, so
yeah,
it's going to be near these red wires.
Yeah. Mm-hmm.
But does it say S16 on it somewhere?
I wish. No, you bring a lot of good common sense to this. For some reason, I don't know, sometimes in automotive we do things that, like when I was brand new, I'd be like, this should be labeled. And then years after being, on the inside, how many years have you done on the inside? It's like, this is just how it is. And I lose my ability to come up with common sense from an external perspective. This should be labeled S16, but it's not. No. The cool thing is you can go in service information, the component locator, and be like, where is S16? A lot of times it'll give you a view of it, and you'll be like, oh, that one's S16. But you're not going to get down there and have it conveniently labeled, unfortunately. No, sadly. Which kind of sucks, but also a lot of things that make your job difficult, you get frustrated with, but it also makes it so that people can't do it themselves, which probably means that's part of the reason that you have the job anyway. Like if it was that easy, people would be like, no, I don't. If it was that easy, they'd be like, I don't need you. Like, I'll just go look for S16 myself, but they can't find it. And a lot of it too is information. If you don't have the wiring diagram, you got no chance. So if you don't have the wiring diagram and the component locator, you don't know about S16, and you also don't know where S16 is, and you have no idea what to do. So you roll into O'Reilly's, and you're just like, hey, sell me a part. Let me put this part in there. Oh, it didn't fix it. Let me bust out the shotgun. Maybe let me go to AutoZone. Maybe they know, hey, Mike, this thing doesn't work. What does it need? And they're like, well, yeah, you should buy this thing. And he's like, but nobody tested anything. Nobody even knew what junction connector S16 was. And they definitely didn't trace it. They definitely didn't even know where S16 was. And they also didn't use the meter. So like, see, there's a big difference between diagnosis and just guessing. Like if you roll up to the car and it's got something wrong, you have no idea what's really. You might have some idea, but you don't know what's wrong, as a matter of fact. You can just make some guesses.
One more question about it.
Okay.
All right. You know how they have all everything's computerized now.
Sure.
And it says you have to get the S16.
Yeah.
You just push a button, be close to it, and it flashes.
Okay. Now you're thinking like a manufacturer tech. So yeah, on the OEM one, I'm going to show you in the Toyota and Honda system. at least in the Toyota system. Yes. But remember, in all data buys the information, all data pro demand, Identifix, whatever, they're all the same. They don't have the information. They go to the manufacturer, and the manufacturer, they say, hey, we need the wiring diagram. And the manufacturer's like, cool, we'll give it to you as a PDF. And then they buy it as a PDF, and then they upload it as a PDF. So if you're in all data, it's just a PDF. It doesn't have any interactive ability. But if you're a dealer technician and you have the original service manual, yeah, they do some cool stuff. Like I'll show you, and you'll be like, oh, this is nice. And then you'll realize, I don't want to use all data. I want to use Toyota TIS. And you can if you work at the dealer. But if you work at the mom and pop, you're using all data, and there's no flashing, and there's no guide, and there's no, like, some of that was a really good idea, and the manufacturers have done it. But they do it in their system, and there's no good way to transfer it into all data system, because all the manufacturers, there's a word you guys will learn called proprietary. You heard about that? Proprietary is like, if it's GM's paying engineers and stuff a lot of money, people to develop this, people to design it, people to do all this, people, in hundreds of thousands, millions of dollars realistically to design and build out and design. But then it's theirs, because they designed it, right? So they're going to use their own proprietary method, their own proprietary software, their own proprietary thing. Like, I have not even the slightest clue how the system would allow you to click on a splice and flash red and then pop up with a connector end view and then pop up with a locator. But there's some sort of programming tool, and it's not just ChatGPT. It's like something that they develop in-house. And theirs is different than Ford's. And Ford's is different than Honda. And Honda's is different than Nissan. And so, like, all that is like, yeah, we don't have a way to, like, make all this work. So boom, there you go. You just get the basic PDF, sadly. But it is what it is. Okay. I think overall, this was a good basic one, knowing which terminals to test. And more simple, so we'll focus on some more simple things coming up. Now this one, you'll notice, has got a little bit of additional things. So the first thing I notice is, if I were to look at that ground, remember this is the chassis ground, this is giving it a name, G307. I meant to underline that, not cross it off. If I'm looking for G307, that's another thing. I'd be like, hey, you know what? If this thing, body control module, doesn't work, don't you think it's possible it could be a bad ground? Yes. Well, let's check the ground. How? Well, maybe we put our red lead on the B plus and we put our black lead on the ground, and that way we could check it. There's a few different ways, right? But let's just say for now we do available voltage. This should have 0 volts at number 3. And let's just say it didn't have 0 volts at number 3. We know that it could be in this circuit. It could be G307. Where the heck is G307? That's when you do the component locator. Not just a ground G307 specifically. That's a specific ground. You don't just go and check all the grounds. There's like a bajillion grounds. So you're going to go for G307, and then you can find it. You could test it. You could unbolt it. You could repair it. You could do whatever. But see, they have numbers. Now, similarly, if you look, this one got just a little complicated, because X is connector. So if it's X6, that's connector 6. X5 is connector 5. X1 is connector 1. X7 is connector 7. Well, if we're up to 7, and by the way, just because we didn't see 2 and 3 and 4 doesn't mean they're not there. It means connectors 2, 3, and 4 are there, but none of these wires happen to go through X2, X3, X4. So they're in there somewhere. That means if you were to find this thing, the body control module, it's going to have at least 7 connectors going into it. Understand? Those 7 connectors are going to have any number of different terminals. Let's say on average, each connector has 20 terminals. How many wires are going to this body control module? There's 7 connectors with 20 terminals apiece. That's 140 wires. That's totally normal for a body control module. This is the computer that controls all the electrical stuff for the body. So headlights, taillights, horn, wipers, windows, keyless entry stuff, wire to other modules to tell other modules what's happening. All sorts of stuff are going to go to this body control module. So the thing is, if you were after this ground, if you thought this body control module had an issue because the ground was no good, yeah, you need to find terminal 3, but it's terminal 3 of connector X6. So you need to find connector X6. Then you need to look. So first you got to find out which connector that is. Then once you find that out, sometimes it's cool because there'll be different colors. Like maybe 1 is red and 2 is white and 3 is blue. And if we're looking at number 3, then you look for the blue plastic connector. Then you got to look for terminal number 3. So you'd have to look at the connector end view, and it might be like all these wires. Which one is terminal 3? Well, maybe it's right there. And then you double check and make sure it's black. And then be like, okay, yeah, I definitely got the right wire. So one guy I worked with on the railroad, so automotive life for a lot of years, and then railroad life was a little bit different, diesel mechanic type of stuff. One guy I worked with was from England, and he was a professional technician. So I was kind of like, well, that's interesting. Tell me like what your job was like. And I thought it might be different. The words that I remember, it wasn't really a profound statement, but it helped me to see like, okay, we're the same. The words he said that I'll never forget were like, I waste most of my day trying to figure out what pin it is and trying to find that pin. He meant terminals. So there's a little bit of like, some people would call them pins and I would call them terminals. So I'm a little more by the book. What he means by that is terminal number 3 is pin 3. So the whole time he knows like, all right, to check the ground, I got to check pin 3, terminal 3. But he spends a lot of time trying to get the information for which connector it's in, where is the connector, terminal number, and then making sure he's got the printout of the connector end view so he can find number 3. And so it was just funny. That was the thing that he brought up. Like he spends a lot of time looking for the right terminal. So just so you know, this is a thing. And you're going to have to get good at it. And it can be kind of irritating, especially when it's a whole body control module and there's 120 wires going to it. Kind of makes sense? And so depending on your path, you might shy away from electro a little bit, but I wouldn't recommend it, and I didn't. And I specifically recall one of the first big electrical problem jobs I got was a Corvette at the dealer. It was a Corvette with a message on the dash, speed limited to 80 miles an hour, service StabiliTrak system. And I was like, oh, okay, check. It's got a whole bunch of codes related to StabiliTrak, ABS, wheel speed, all sorts of stuff like that. I'm like, all right. Well, if it's got a whole bunch of codes, I start to look at the diagrams. And you know what I notice they all have in common? They all go to the same module. And it's the traction control module. So I'm like, okay, if they all share the same module, maybe I better look at the module. Would that be kind of logical? So I'm all ready, fresh out of school, got all my highlighters, all my little markers in my pocket. I learned it in school. I get the wiring diagram. I am ready to trace the wiring diagram to the max. But then I'm sort of like, let me just look at this module. The module was in the trunk, and this is a convertible car. And when I went to look at the module was, shall we say, underwater. The whole trunk was full of water. So I was like, oh, well, that's what's wrong with it. The module's underwater. Computers, they don't like to be underwater. You know, typically you want to find out what the thing is made to do and then let it function in that way. So like a lawnmower. Do you know what a lawnmower is good at? Cutting grass. Do you want to be a lawnmower? You can chew the grass. Like, it's just not what you're good at, right? Modules don't make good swimmers or submarines or anything underwater. So it's like, oh, the module is underwater, first I got to figure out the source of the problem, right? The source of the problem is why is there water in the trunk? So I had to figure out the water leak, and I did. It was a little vent for when you close the doors, it's got to let air go out. So there's a vent right there that was messed up and water was getting all in. So once I figured out that, then it was like, you think the computer's going to survive? You put it in rice? No, it's done. But then the bigger problem was all those wires, like 120 wires, were all underwater. So what do you think the status of those nice little metal terminals is? Yes. So you got a couple options. One, do the whole harness of the vehicle, which from what I recall is about, for the StabiliTrak related ABS harness, it was about $3,000 for the parts. And then it was going to be a whole bunch of labor to pull all sorts of interior panels and the carpet up and all this stuff. Or repin that connector. So you could carefully remove the terminals, cut that off, crimp a new terminal on, and reinsert in the correct location. That doesn't sound hard, but when there's that many wires, I'm gonna tell you, it was a little bit rough. So knowing where all these terminals are is necessary when you got to test it, but also just in the case that you need to do a repair, like I find out pretty early, like, hey, I've got to repair all these terminals. And I spent like a couple of days, whole days, not like class periods, like whole work days. Terminal, crimp, cut, terminal, crimp, cut, unpin it, repin it, unpin it. It was fun. You know the funnest part? What was the customer concern? Well, the original one was the vehicle displays a speed limited to 80 miles an hour service StabiliTrak. So after I service the StabiliTrak, what do I have to do? Yeah, I had to clear some stuff. I had to program a new code, but how would I verify that it's no longer... Oh, yeah. That was fun. What'd you do? Well, I had to make sure it would go over 80 in the customer's Corvette. Oh. However, just so you know, if you do get pulled over and you're like, officer, it had a service StabiliTrak, do not exceed 80. I had to do 81 miles an hour to make sure the car's fixed. You're still going to get your ticket. I'm just letting you know. Okay. No more details on that particular vehicle. It was a fun time. It was a hard one to fix, but it was a fun time. All right. And then if you look even lower, like for example, do you see the B plus right here? What do you think you'd expect on B plus? Yeah, like that would be a positive, right? That'd be 12 volts or so, right? So what's kind of cool is if you look, sometimes it's labeled. You could see B plus, oh, that means I should get 12 volts or so on terminal 4 of X5. And then ground, I should get 0 volts on terminal 3. So like if this whole body control module didn't power up, I try to communicate and I can't communicate with it and it doesn't appear to be powered up, the first things I would check would be 12 volts on terminal 4 and ground on terminal 3. Like if your computer doesn't turn on, you make sure it's plugged in, right? That's it. I mean, some of this isn't rocket science. It's just when you tell the customer, yeah, I need to make sure that it's got power, they think that you're going to walk over to the wall and you're going to look at the outlet and be like, is it plugged in? Like that. That's not like that. How it really is, you're going to look at the wiring diagram and be like, where does it get the power? Oh, terminal 4 of connector X5, and where is that, and where is it located, and then how am I going to check it, and what connector end view, right? And then how does it get ground? Terminal 3 of connector S6. You may very well spend an hour making sure it has 12 volts on 4 and ground on 3 because you got to pull the diagram. You got to locate those connectors. Which connector is X5? Which connector is X6? Which terminal is which? Crawl up under there, upside down, and make sure, right? So the way we write stuff should be a little more technical in nature. Not, I made sure it had power, because the customer is going to visualize you walking over to the outlet. If you really looked at how you did it, retrieved wiring diagram, traced wiring diagram, found it should have 12 volts on terminal 4 of X5, should have 0 volts on terminal 3 of X6, used the meter, did available voltage at these multiple points, then the customer's like, all right, fine, take my money. But if you say checked for power, They're going to be like, why am I paying you mechanics? You're so shady and you're shisty and you're ripping us off. And be like, fine, I don't even want to get involved in your crappy water leak on your Corvette. Like, get it out of here. Take it someplace else. I would. Cut it loose. Uh-huh.
Just going in and you're starting this job
Yeah.
as a technician. I know you're not going to start off with.
No, for
Does
sure.
someone like walk you through when you get to that point and you have to do that, like
It,
a senior technician?
yeah, so I did 2.5 years as an apprentice. So I had been along somebody's side for over 2 years before I was promoted to make line tech money. And then once you're line tech money, like, 30, what's the number now? $34 an hour, you're going to get some stuff like this. And if you want the big bucks, you can't really be like, well, I want to get paid really good, but I also want somebody to hold my hand. See what I mean? So for 2.5 years, I had the hand, and I'd be like, Steve, what should I do? And he'd be like, oh, well, do this, do that, do that. But then when I was like, hey, give me the big bucks, I'm like, Steve, and he's like, no, you're a line tech. I'm out. Right. So to be really honest, this was I say like one of my earliest electrical jobs, but that was a few years into working every day, 40 hours a week. It was a few years, but I was no longer an apprentice. So this was like very memorable to me. A lot of the stuff I did under my mentor, I don't really recall that well, because like it was really his job. I was there like helping, so I was like, whatever, he tells me what to do and I do the thing. I'll be, let me put my music in. I don't really care. But then once it was like, no, this is your thing. You're diagnosing it. You're fixing it. You're writing it up. And if it doesn't fix it, you're going to be the one in the manager's office. It just got a lot more serious.
By the time you got to that point,
I was ready.
pretty strong.
Yeah.
Like
Yeah. I mean, I knew what to do. It was like if you ride the bike with the training wheels for long enough and like ultimately you're like, yeah, I could ride this bike. You're just a little shy to take the training wheels off. The training wheels had to come off. And then I was like, yeah, I could do this. There's a lot of learning experience, but just so you know, electrical can be pretty intense, but it can make pretty good money. So I had a student tell me something kind of funny yesterday, and it's sort of like changed the way I'm looking at it. Like, none of you have to know how to do this. You can not know anything about it, but the way the free market works, if you want the money, you know what they say, more money, more problems, right? I mean, I think the context is different. It's more like if you had a lot of money, you're going to run into a lot more problems. Like people are going to try to be your fake friend when they're not your real friend. Whereas if you have no money, you know who your real friends are. But I'm going to reword that context. If you want more money, you got to be able to solve more problems. And trust me, there's plenty of problems that need to be solved, right? So like for me, when I was younger, I wanted to do this type of work because I really wanted the money. And then the better you get at it, the more problems, some more problems, some more problems. And then you're kind of like, well, look, this is ridiculous. I'm doing all these ridiculous problems, re-terminaling 120 connectors. Like, you're going to have to pay more. And then they're sort of like, yeah, we will, because nobody else will do it. And then next thing you know, more money and more money and more problems and more problems, but more money. So it depends on what you want. If you want to just be able to like chill and, chill is a term that I would delete from my vocabulary if I was you. But if you want to be chill, don't get good at this. If you want more money, get good at this. And then, you'll deal with this type of stuff. So you all know, all right? But my job is to get you so you can understand it, so you can make the decision if you want to do it or not. I don't want to be like, yeah, you took electrical, but I sugarcoated it and made it seem like it was easy, because it's tough. That's my honest answer. Very good. All right, here we go. Look at these wiring diagrams. These wiring diagrams show something new. And if I look at it, well, we can recognize a few things. So we're just building like one layer on top of the next, right? I'll use red. Right here, there's a black and green. Here we got the terminal numbers. But if you notice, C1023. That's my point. C1023. Or up here, CLS30. Or over here, C1043. They're not talking about connectors there. They're talking about circuit numbers. So each of these circuits, like this one, for example, C110, sometimes they'll show you a circuit number. And the main reason for this, it's not so much just for you. It's, let's say you got one of those difficult cars, right? So let's say, like I was saying, you're a lube tech, you show up to work every day and they realize you can actually function and you're not going to give a bunch of home drama and say you couldn't come into work because your grandma died for the third time and whatnot. Let's say they promote you from a lube tech to an apprentice, then you spend a bunch of time really learning the trade. Typical apprenticeship could be like, 3,000 to 5,000 hours. Then they go ahead and they make you a line technician. You still have problems. You still don't know everything. So let's say you're working on this and you're very lost and it's like, this is a mess and I've done the best I could. You could make a call to TechLine, some sort of technical assistance center, and be like, hey, I'm checking this circuit and this is what I got. And they're going to be like, what circuit? And you're going to be like, do you see the purple wire where it comes over and the purple wire does this and the thing? No. Don't be confusing. How about you tell the technical assistants S109? And they're like, okay, cool, I see S109. See, so it's nice when you can have a circuit that's labeled. So if you call some sort of technical assistance or somebody's trying to help you remotely, you can be like, yeah, we're talking about circuit S109 here. But not every manufacturer does it. But if you do see a weird thing like, that was the splice. It was C110. So I got myself, I was reading the numbers and I wasn't paying attention. This is circuit C110. S109 is the splice. C110 that's underlined, that's the actual circuit number. Or if you're over here on the communications lines, VDB08, VDB04, or VDB05, right? So it's kind of nice if they have a circuit number. The other thing they've done with the service information is sometimes they'll have a document ID. So if you're following service information, there's a document ID and you're talking with some TechLine, technical assistance, tasks, whatever, they have a lot of names, and you're like, what document are you referring to? And you'd be like, oh, it's document ID ABC123. And that way you can be looking at it, they can be looking at it, because sometimes fixing the cars is actually pretty tough. So you might need some outside help and you could be on the same page. All right, that was pretty fun. But other than that, a lot of this was kind of the same, but to make a good activity, I don't know if you guys can see, it's a little zoomed. I might be able to zoom in. I can zoom in this look. So look, let's go with a side lamp, left front. What type of voltage would you expect on terminal 1? Just based on the color, can you tell? Probably 0. Yeah, so we should have 0 right here. Right, and this black and green is most likely going to ground. Now, to make sure, we'd have to actually trace the diagram, really follow it, but I'm pretty sure. Which means, what do you think we expect to have on terminal 2? Don't you think that should be 12 volts, right? So we're expecting 12 volts on circuit C1127. We're expecting 0 volts on circuit C1127 on the ground side. It's all part of the same circuit. Or it could be CLS30, actually. let me look at that. CLS30. Yeah, this is trying to call out the connector number. I missed that. The circuit is CLS30. Cool. Not bad. All right. No, let me change over to this and zoom back out. Yes, very nice. You're going to have so much fun doing wire diagrams, let me tell you. Tons of fun. Okay. Now, when it comes to reading that wiring diagram, I've shown you a lot of basics, but the nice thing is, if you're doing a vehicle specific, somewhere in service information, there's going to be a key and a glossary and some symbols and some things like that. So this one, for example, the battery looks slightly different, capacitor looks slightly different. In this example, this is the cigarette lighter, so they could vary in symbols. If you were to go back in the day, the service manual was in print, and like some of the early pages would be the key. It was really easy to find that. Now it can be a little bit tougher to find the key in the glossary of terms and whatnot, but just know it's there somewhere if you do need it. If you're really not sure what a symbol is, you could look that up. Cool. And then here was some examples of these are Toyota specific diagrams, or these are Toyota specific symbols. So just to remember, switches, relays, solenoids, diodes, capacitors. You saw this screen when we were doing overview, but just as a refresher, because we're going to jump into some wiring diagrams where you need to know these things. The one that people most likely tend to forget are the transistors. So if we just review a transistor, because we may experience some of those in the diagrams, let's look at making an NPN. We would have a ground going here, but right now the ground is open. What would we need to do to close the ground solid state switch? We need to give some voltage here. And then once we give the voltage there, it changes the solid state to allow the ground to continue and actually go to ground, right? So just keep that in mind in a transistor. If you don't have the 12 volts on the base, you don't have the ground flowing through. Or it could be the other way. We could have positive trying to come through here, but the positive won't go through the base until it gets a negative on the base, at which point the positive, that's the wrong color, the positive will travel through. It's kind of showing a little bit opposite because it's electron theory, right? But just keep that in mind with your transistors. If they've got the base current, it'll flow. If it doesn't have the base current, it won't flow. And other than that, you can pretty much, like honestly with this, we could have pretty much drawn it as a switch, right? The switch is open, but if we give a base current, the switch becomes closed. Cool? Not a real big thing. All right, here's a full actual wiring diagram. Do you like the colors? All right, you don't always get the colors, but right now you got the colors. So let's do how I would approach this. I always start with, well, probably just zooming out, taking a look at the picture. What are we even looking at here? What type of diagram you think this is? It looks like something with lights, right? What do those lights say? Yeah, the backups, the reverse or the backup lamps, exactly. Now, if we were to look at this, let's start with, what do you think I want to start with? The loads. Let's start with the load, and let's make the loads yellow. Where are the loads? You know that's the bulb, right? Here are the loads. Okay. The control device or devices. What do you think the control devices are? Yes, let's make those like light blue. How about that? This one and or this one. Now here's what's interesting. It's kind of like it could go one way or the other, but here's a little detail that we got to look at. Can you see that letter, those letters and this letters? AT or MT. Do you know what that means? AT or MT? What do you think? All right, if you bought a brand new Mustang, would you get the AT or the MT?
MT. Facility. Gotta get MT.
So, which one do you want to trace? Right? Because remember, the cars are kind of the same, but when you have an automatic and a manual, they're a little different because you put the manual in reverse like this, and you put the automatic in reverse like this. So they have different switches. They have a different transmission. But the diagram shows both, so you get to pick which one. We'll trace them both, but pick one first. All right, let's pick the manual. All right, if it's a manual, this is the control device over here. So I'm going to delete what we did. I don't know if I can actually. We're going to get rid of that, and we're just going to do the manual. That's the control device. That's it. That turns it on and off. That's all. So let's say from there, I'll give you a couple of hints. If you wanted to trace this, the first thing I do is identify the load. Coming into the load, we should have a 12 volts. Going out of the load afterwards, we should end up having a ground. So if you kind of think about it like that, we could start with where the power actually comes from, which is ultimately the battery, but it doesn't show the battery here. So it says IG. Do you know what IG means? It's not Instagram. Ignition. So that means when your ignition key is turned on, this gets power. If your key is off, it doesn't. So that would indicate, okay, I need to turn the key on to test this. Click, click, 2 clicks. Ignition on. And then voltage should go through the gauge fuse number 1. It should go through EA1, which is a connector, through CA2, which is a connector. What's that stop sign thing?
To decide which way to go.
It's a splice. Yeah, that's it. Good point. But remember, we're not going to draw this side because we don't care. It's not because the manual's better. It's just because we don't care right now because it doesn't have that. Now, I got a little too far here. I actually should go right to here. Currently, we won't have any voltage down here. Do you know why? Right, so what should we do to test the backup lights? Yeah, how do we close the switch? Sometimes it's a thing, sometimes, but in this case, how does the vehicle know you're in reverse? You got to actually click the shifter in reverse. When you move that shifter in reverse, it moves a rail in the transmission, and the rail in the transmission pushes on a little switch. That's how it knows it's in reverse. So logically, to test the reverse lights, you'd need to put the car in reverse. If you don't put the car in reverse, the reverse lights aren't going to work. There's nothing to test. So we put the car in reverse, and that's why it's nice. You can do it key on, engine off. You understand? So you don't put the car in reverse with the engine running and then let your foot off the clutch and get out and run yourself over. Just do the key on, engine off. Okay, cool. And then when we close the switch, we should have voltage coming all the way down, all the way up, and it would go that way, but we don't care. CA2, AE3, a junction, EN1, SN1, a junction to the bulb, and to the bulb. Okay, at that point, the load should consume the voltage, leaving about 0 left over, and so this should all be ground all the way to the chassis, both sides. That would be the correctly traced backup lamp circuit. And then if we've correctly traced that, this is where I'm going to try to show you the value in tracing it. Although, to be honest, once you have a lot of experience, sometimes we don't always trace it. You can kind of just visually see and be like, oh yeah, I know where it should have 12 volts. But when you're new, you really want to trace it, especially so you don't get yourself confused. Let's just say, you understand the colors, right? So everywhere that's red should have about 12 volts-ish. We don't really care about if it's 12.6 and 12.5 and 12.4, right? When we're understanding exactly how electricity works, we gain an understanding that, hey, you might drop 0.1 volts going across to connector or a switch or a fuse you might drop a little bit of voltage here and there, but if you're dropping 0.1 here and there, it's not going to make the bulbs not work, right? Or be dim. We'd be worried about if you're dropping more than a half a volt somewhere. So with that being said, what should my voltage be here? Yeah, how about here? How about here? How about here? How about there? Right? Once you have it traced, you're like 12, 12, 12, 12, 12. You can do your test quickly. What should I have here? Ground, yeah, 0, 0, 0, 0. All right, right? So that's what we should have. Now, let's say I jump on the car and I get a measurement of 0. What are your thoughts? Potentially, yeah. Technically, it could be anywhere between EA1. Well, technically, it could even be up to IG. If we had a problem with the ignition switch, that would mean it wouldn't get voltage down to that fuse. But if we had a problem with the ignition switch, probably a bunch of things wouldn't get powered up. So it'd be like, probably a slightly different concern, which is why I normally start with zoom out. If the windows don't work and the radio doesn't power on and a whole bunch of stuff doesn't work, I wouldn't probably pursue the reverse lights. I'd probably be like, why is all this stuff not working? And then I'd probably find a different wiring diagram, like the power source diagram, which shows me how does the ignition power, what does that go through to give ignition power to a bunch of stuff, right? But yeah, I would say if we started, and let's say my first measurement was right here, and I got a 12, and then I got a 0 there. Yeah, I'd say it could be the fuse. Technically, couldn't it be this connector right here? Right, so we got to get it all the way narrowed down. So probably what I would do is I would say, let's go to this point, and let's say I agree with what Tracy said, and we've got also 0 up here. Then yeah, we're pretty much at the fuse at that point, right? So wherever it goes from 12 to 0, it's between those 2 points. Cool. So if this was available voltage and I got 12 and available voltage and I got 0, we know what we got. But the other thing we could have done is we could have drug our meter lead down here like this, our green lead right there, our black lead, and we could have put our red lead up here, and that would just be a voltage drop measurement. And if we got a 12, you'd be like, why am I dropping 12 volts across the fuse? That's because the fuse is open. Make sense? All right, but let's say I got a different number now. Let's say that we fixed that one. We won't give any details as to how we fixed it, but we repaired it. Let's say I've got, let's go with, I got a different color. Well, I'll go with this. I got 12 here. I got a 0 here. What do you think? Yeah, the switch is open, but what if I make sure the car's in reverse and the switch is still open? Yeah, there you go. So get a new switch. You'd be like, hi, I diagnosed your vehicle, and yeah, you have a defective backup lamp switch. You get a price from the parts store. You get a labor time, which you can look up on AllData, or you can sometimes kind of make it up. Be like, yeah, I charged you 1 hour for the diagnosis, and I diagnosed it as a bad switch. And they're like, what? You charged me an hour just to tell me the switch was bad? And be like, well, you're welcome to do it yourself. What I need to do, I need to pull the wiring diagram. I need to look up the terminal numbers. I need to test different points. I need to interpret my readings. And then, yes, I confirmed it's your switch. And they'd be like, oh, yeah, I don't know how to do all that. So, okay, take my money. That's pretty much how the conversation goes. But you got to be able to use your words and explain why you're taking their money. What diagnosis doesn't look like is, well, it could be the switch. So, hey, we should replace the switch and see if it happens to fix it. You can do business like that, but that's not diagnosis. See what I'm saying? That's just like educated guessing. Makes sense? Which is fine, but I don't think you should charge for guessing. But if you measured 12 and 0, you know the switch is bad. You verified that it's in reverse, but you know the switch is the problem. So when you call them and you tell them it's going to be this, this, and this price, and then they okay it, and then they're like, yeah, go ahead and fix it. It's going to be $100 for diag, $100 for replacement, and the switch is $25. You're looking at $225. That's why the bill is what it is. It's like, I can buy that switch for $25. Yeah, but you didn't know it was the switch. And, you know, most of that was really a diagnosis. The install is not that technical. You could unscrew the switch and screw the new switch in there. The diagnosis is where I'd put my focus because there's not that many people that could do it, right? So it's job security. Good. And then, of course, you'd have to put it in reverse and verify the reverse lamps work. But let's say this is a very rare instance where you put the switch in, it still doesn't work. And so you retest your numbers, and now with in reverse, you got 12 volts down here now. Did the switch fix that problem? It had 0 volts coming out of it. Now you replace the switch and it has 12 volts. Now the switch is good. But what if the lights still don't work? Guess what that tells me? The problem's down here, right? Because I got 12 volts make it to this point, but if the lights aren't working, the problem's down here somewhere. Is it on the positive or the negative? I don't really know. So sometimes what I'll do, to be honest, is I'll just start way back here. What should I have at this point? All right, what if I have 12 right there? What should I have at this point? What if it has 12 volts down here also? How can it have 12 volts where it's green? It's not supposed to. Anybody remember this? What if my junction connector was open? The 12 volts will go through the load and go to the open. And then down here, I would have ground, right? So if I had 12 volts right there and I did one more test, right? And that's why electrical is cool. There's no steps to follow. You can kind of make them up. If I test terminal 9 and I have 0 volts, but I tested the terminal going into the junction connector and I had 12, that's an open junction connector. So that's not a switch. The switch wasn't going to fix this car. If you were to really look at this system, you could have a bad fuse, a bad wire, FA1 connector could be bad, a bad wire here, CA2 connector could be bad, this splice could be bad, this black wire could be bad. You could have a poor connection at terminal 2, a poor connection at terminal 1, bad switch contacts. This wire, blue wire, could be bad. This connector could have a bad male and female pin fit. This wire could be open. AE3 could have maybe corroded terminals. E48 junction connector could be underwater and corroded. This wire could be bad. EN1 could be disconnected. This red wire could be cut. SN1 could be maybe caught on fire and burnt, and now there's a lot of resistance due to the burnt metal and deformed plastic. You could have a bad S16 junction connector. You could have 2 blown bulbs. You could have a bad connection on the ground here. You could have an open wire. Well, actually, if you had an open wire here, what would that make? Only this bulb wouldn't work, but this bulb would. So it couldn't be there, but it could be here. You could have a bad splice. You have a bad wire here. You could have this bad junction connector like we said. You have a bad wire here. You could have a bad ground at the chassis, S1. You understand why you don't want to play the guessing game. How many times you going to guess before they're like, no, I need to take it to somebody else who's a better guesser. You need to take it to the psychic. Oh, let me see your hand. Oh, yeah, it's an open at S15. Like, that's not how it works. It's just not. If you don't physically do the measurements, you literally don't know. It's a guess. It's the way it is. All right. So hopefully that wasn't too intimidating, because that was actually that's a fairly simple diagram. Now let's say you get a little older, you get a little more tired, and you're like, you know what? I don't want the manual anymore. I want the automatic. All right, fine. We can do that. If you wanted to trace the automatic, it's going to start off kind of the same. Red to here. We don't care about down. We care about over. Red to here. Now, what's going on here? This is park neutral position switch. Do you know what that means? Prindle. Yeah, the Prindle. We could call it the Prindle. You grab the shifter. You take it out of park. You remove it to reverse. It just goes click. The switch isn't usually there on the shifter. The switch is normally down on the transmission, but when you move the shifter, it moves a cable, which moves a shift, which moves a shift shaft, which moves a manual valve in the transmission, but there's also a switch right there, and you're actually moving the switch down on the transmission. When you were in park, these are not connected. When are they connected? What's that say? Yeah, they're only connected in reverse. So if you want to test this switch, You got to put it in what that says, which is reverse. When it's in reverse, then it should go through and it should connect RB to RL, and then red should go like this. Once it hits the loads, it should change over to ground. Right there. Consider that one traced. And then the method, which we're going to mostly focus on tracing now, but the method would be the same. If you trace it and then you go to poke and do diagrams and back probing and whatever, all you really got to do is look at the color. And if the color's red, it should be source voltage. And if the color's green, it should be ground. And if you get a 0 voltage reading on something that's highlighted red, something's wrong. Kind of makes sense? Like power's not making it to that point. Cool. So if we had a 0, right, I don't know, how about here? I know something's wrong. Is the problem down here? No. The problem, if I have 0 volts on red, it means it's not making it to there. So the problem's somewhere in here. So now just go back and let's say I have 0, 0, 0, 0, 0, 12. Then I'm like, oh, what's between the 12 and the 0? The Prindle or the park neutral, the neutral safety switch. And be like, all right, found the problem. There it is. Make sure it's not out of adjustment. But you see what I'm saying? It's not really that difficult, I don't think. But you got to be able to trace the thing. Then, of course, later we get into back probing. That's a slightly different skill, but you should be getting there. How'd you feel on that? Was that diagram hard? Not there.
Did you replace the whole, that's like some type of switch too?
Exactly. So you'd say like, oh, this is what I diagnosed it as, and then you may have to go and like call parts, or if you're in a dealer, a bigger shop, you may go to the parts person and be like, hey, I need this park neutral position switch, and they'll be like, oh yeah, okay, that's this and this and this, and here's how much it is. So you can get a little help from parts when you are not totally familiar with what the part is, but you'd also probably lift it and visually inspect it and be like, oh yeah, it's this thing. I see the wire goes into it and the wire comes back out of it, but the voltage is coming in, but the voltage isn't coming back out. There's something wrong inside that switch. We don't like dissect it and try to like clean terminals. We just like, it's in the switch, sell the switch, and then you put the switch in, and then it fixes the car. A little bigger, yeah, like about this big. Like typically about that big. The manual one's gonna be like this. It's just gonna be literally screwed into the case. The reason that the neutral safety switch is a little bigger is because there's gonna be like probably about 6 to 10 wires going through there, because there's a circuit for telling if it's in park, there's a circuit for telling if it's in neutral, there's a circuit for telling if it's in reverse, and then typically for drive and any of the lower gears, so that way it can tell what your shifter position is. On a new car, they'd call it most likely the range switch. You want to know what's horrible though, honestly? On some of the newer ones, they started putting the switch inside the transmission. So if you have a bad reverse switch inside of the range switch, you'd be like, yeah, your reverse lights don't work because of the range switch, but it's inside the transmission. So we got to pull your transmission out, take it all apart, replace the switch. And then you're like, the engineers just hate us, or like, why put it in there? All these years it was fine outside, and then you're like, oh, I know, we'll put it inside there. Like, oh, thank you. I think the logic was in the snowy, rusty, salty areas, if it's inside the transmission, it doesn't get corroded, but like seriously, just don't put it in there. Please. Why is it in there? And so there you have it. All right, pretty good. So that was your typical diagram. And then, of course, there's, some others that we'll do and some details. And so if we look at this one and we were to do kind of the same thing, we could pick the loads. Last time I think we made them yellow. So be like, oh, what's the load? The fog light and the fog light. But this one has another load, doesn't it? The fog relay coil. Oh. Then if we look into the control device or devices, it's really this. In this thing, we're calling the dimmer switch, or it may really be like a multi-function switch. But technically, this one's a control device as well, because there's a switch in the relay, right? So This diagram gets just maybe slightly more complicated, but not bad. All right, so if we're looking at this, I would say it's pretty safe to assume we got an issue with the fog lights here. So if I had an issue with the fog lights, what position should I put the switch in to test the fog lights? I agree with on. All right. So if it's on, now you can see on is going to connect BFG to LFG. All right, if that's the case, then let's go ahead and we'll do a basic trace. Red coming from I don't know where. In this case, it wasn't particularly relevant. Through the fog lamp fuse. Well, actually, then it stops right there, doesn't it? Interesting. Because the switch is open, correct? How would we turn this? How would we close the switch contacts in the relay? Well, we've also got to worry about this red through this fuse. Here, 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 here. And then it should really stop at that coil relay, or that relay coil, which means technically I would be expecting ground on the bottom side. So let's see if the ground will trace out. It goes to BFG. Oh, wait, but we have the fog light switch on, so guess what it does? It's connected. So it then goes down to HL. Interesting. And HL actually won't make any connection unless we have the dimmer switch in a certain position. Can you tell where we need to put the dimmer switch? It would need to be, if this is where the out is, and we want to make it to out, it would need to be in low. Do you know why it would need to be in low? I can tell you. Right. If you ever notice, most cars, when you put the high beams on, the fog lights go off because you don't want too much light to blind the other drivers. Or if you turn the headlights off, the fog lights are off. If you want the fog lights on a modern vehicle, you need to turn the headlights on, and they need to be in low. And then you'll actually have ground path all the way through. So if you have headlights on in low and your fog light switch on, this ground will make it up like this, over through the switch in a couple different ways, and then the ground will go to the bottom side of the relay. What happens if that coil relay coil gets 12 volts on one and ground on two? What's it going to do? Bingo. So if it closes the switch, now we're really talking. If it closes the switch, that means this is closed, which then means what's going to happen to the 12 volts? It's going to pass through. And it's going to go hit the fog lights right there. At that point, that's going to stop. And then on the bottom side of the load, it should be ground and ground. That's your correctly traced circuit. Okay, make sense? Then, because we looked at wiring diagrams quite a bit, remember there's a lot of information on here that's here to help you do your diagnosis. So if I were to erase this and just point a few things out, we'll do the green. This has the fuse labeled. This has a terminal, a terminal, a terminal, a terminal for the fog lights, and the fog lights labeled. This has a connector number 2G, terminal 12, 2R, terminal 4, splice E10, ground EC and EC. These wires are colored, so you know they're colored. We've also got this fuse, which remains unnamed, connector 1, terminal's not labeled. We got this wire harness and connector IF2, 2C. We got EC ground. We've also got this switch, and the terminals are labeled out, 11, 10, and 17, and the wire colors. So let's say we're to do one lesson back to how we did it. If you wanted to tell if there was 12 volts at this wire, you would have to go to the male terminal based on that chevron. Get what I'm saying? Whereas if you wanted to know if you had 12 volts up here, you'd actually have to go to the female terminal on that chevron. See, because it doesn't go top to bottom when you get in the car. It goes any which way. You don't know which way is which. So, right, that was a pretty a pretty good chance so you could see, like, oh, I overdid that one. It's very nice when you can actually tell which way it's coming from. Because if you look at the car, you really don't know. You might guess based on where the fuse was, but you don't really know, right? So that wiring diagram has a whole bunch of cool stuff there. Did you guys understand how the switch worked? Not that hard, I think, but if you don't, we can cover it some more. But if you feel good, we'll roll it. All right. So this is Toyota specific, but I think you'll learn to like it. It's showing you like you can navigate this wiring diagram, and I'm going to show you this on another screen. It's showing you all the diagrams you could pull up. So some of this is like when you want to check the terminals, you got to find the pins, right? Like the guy told me at work. You got to actually find the correct wiring diagram. Then you got to navigate to whatever the thing is that doesn't work. So like if it was this one, let's say whatever that is, actually it's too zoomed in, I can't really tell, but let's say that this motor didn't work. If you want to diagnose this motor right here, right where the hand is, you'd have to find this diagram first, right? Actually, I think that's the starter. Yeah, that's the starter motor. So if the car's got a no crank, you go to start it and it won't start. This is giving you the diagram like, hey, this wire goes to the starter here. That's the big positive battery terminal. And the ground is right here on the case. And then this right here is a starter relay. So this is the small solenoid wire, right? So if you wanted to diagnose something, you got to sort of know which diagram to go on. And then sometimes the diagrams are interactive and they can give you like connector end views and whatnot. And if they aren't, you got to dig them up. So I'll show you some examples of that. Cool. Now let's say this is a simple diagram, right? So we should be able to do this one. Just understanding this is more simplified for tracing practice. When you actually got to get on the car, it's more than just tracing. You got to actually know terminal numbers and stuff so you can go do the test. So we're dialing it back a bit. All right, if we look at this thing, this is an example of what we call a power side controlled circuit. By now, you guys should be able to identify the loads, right? It's 3 bulbs, so we won't do that. We'll jump right into the trace. You want to start positive or you want to start negative? You pick.
Negative.
Ooh, we got a disagreement. All right, I got 2 positives. You're overruled. All right, positive means I'm going to red. I'm going to do highlight. Positive starts at the fuse typically, right? It goes to here. And then truthfully, it goes actually all the way to there, and then it stops. You know why? Switch is open. So if you want to test these, well, look at what they are. Stop lamps. Guess what you got to do? Yeah, somebody's got to step on the pedal. You can also probably use a pry bar, an extension, or a pedal depressor to hold it down. Everything is not a 2-person job. But if we were to hold the pedal down, then what should happen with the red? It should keep going because it's closed. That's right. And then the ground should be pretty easy. Okay. And if you've got it traced like that, then you can go and you can do some pretty quick evaluation, some quick measurements and be like, oh, it could be this thing or that thing. If it was a bad stop lamp switch, how would I know? Yeah, 0 here. You'd press the switch, and if you have 12 going in and you have 0 coming out, the switch has high resistance, no continuity. You could name it many different things, right? Now, what if you looked at this diagram and you traced it like that, and then you realize the problem with the car is that this light works and this light works, but this light no worky. You think it could be the fuse? The switch, this wire, this ground? No. What's it going to be? Exactly. You take a parallel circuit and you break it down into a series circuit. So we know it's got to start here and it's got to end here. Actually, technically, really on the other side. It's really got to end here. It's somewhere between here and here. And that's it, right? And so really, I would just, I mean, if it were me, I would just ignore all this stuff and just be like, in fact, it's technically, that was even wrong. It's really between here and here, and that's it. So if this was a terminal 1 and this was a terminal 2, and let's say I got 0 on terminal 1, then what do I know? Let's say I got 0 right there. Then I know it's really between here and here because I'm not getting any 12 volts down there. Cool. So then, then basically that's it. If I know it's between this splice and this connector, that's as diagnosed as it needs to be. It's on that wire. Whereas let's say I got 12 volts right here. Let's say I got this point 12 volts. That tells me that all this is good. But let's say I went down here and I got, how about 0 volts? What if I got 12 going in and 0 coming out? Yeah, then it's the bulb, exactly. The bulb has 12 volts in ground and it still doesn't work. The employee has everything it needs to do the job and it still doesn't do the job. You get a new employee in there, right? All right, now this is the only one that's a little more confusing. What if I had 12 volts here and I had 12 volts here? You know that I have 0 here, right? Because that bulb works. And I have 0 here because this bulb works. If I had 12 volts after the bulb, what's that tell me? That tells me this ground is open right in here. So it's that wire, right? Get what I'm saying? If you don't have 12 volts coming into the bulb, it's before the bulb. If you have 12 volts making it through the bulb after the bulb, that means that the problem is after the bulb on the ground side. Kind of sort of makes sense. So that was correct, yeah. If you have an open ground, the bulb won't work. 12 volts will go right through the bulb. What if I were to draw it like this? I bet you'd understand it. What if that was an open switch? You see how the bulb wouldn't work? 12 volts would go through the bulb. The bulb wouldn't work. The 12 volts would go through, but there'd be really no current flow. There's no current flow, the bulb doesn't work. So the 12 volts will go all the way to the point of the open. Then if we were to close it, all this 12 volts is gone, and now you have 12 volts in ground and the bulb would light up. So if the switch was open, it wouldn't work, yeah. Of course, there should never be a switch on the ground side like that in that particular instance, but that was the, if I draw it as a switch, you understand what it would do probably a little bit better. All right, so that was the power side controlled. The difference is the switch is on the positive. Okay, so that's pretty common. Here's a ground side. Now you're like, whoa, what the heck? This is different. Well, not really. You guys can see the loads. Load. Oops, I tried to highlight it. Load, 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 load. The control devices. Where are the control devices? There's no switch over here. The switch is on the ground side, the ground side, the ground side, the ground side. Okay? So these are ground side controlled. We give the load ground or we don't give it ground, right? So technically on this system, it's kind of weird, but 12 volts comes through the dome light, goes to the junction, goes to here, goes to the vanity light, goes to the other vanity light, goes to the personal light. Those have 12 volts all the time. Why are they not on?
There's no ground connection.
Bingo, because the switch happens to be located on the ground side and we're not giving it ground, right? So if you wanted to test the vanity light, what would you do to the switch? Yeah, you'd have to close the switch, right? Give it ground. Close the switch. So let's say I draw this closed. Then if you think about what's going to happen, we have ground down here. You know that. The ground's going to make it to here. Now that the switch is closed, this should have a ground and the bulb should glow. But technically on these other ones, the ground would go to this point. I drew it a little too far there. The ground would go to like there. The ground would go to there and to there. But you see this, the bulbs don't have access to ground because the switches are open. Cool? So if you were to look at this with the switch open, these would be some normal measurements I'll throw in there.
So that would be like the mirror that you
Yeah,
pull down.
exactly. They'll send positive to that. They could do it either way. They could put the switch on the positive or the switch on the negative, but yeah, that's what the vanity lights are. Exactly. Right? But in this case, if they're ground side switches, it's a ground side control. What should our voltage be right here? 12. What about if the switch is open? Still 12. Still 12. It's 12 anytime that the key's on or whatever it takes to power this. We don't know because we didn't see where it came from, but anytime the key is on. In fact, actually, this is probably battery. You notice that you can leave a dome light on in a car or the vanity light and it can kill the battery. These are probably battery powered. So we'd have a little label here, BAT. So you probably don't even need to turn the key on. These will get power all the time, but the switches stop them from getting ground, right? So that should have 12 volts. Now this one that's open will have 12 volts all the way to the bulb, and it would even have 12 volts on the other side of the bulb, but it just wouldn't have any ground on the other side of the bulb. And that's where these are a little special. So ground side controlled will have 12 volts all the time, and then it'll either get ground or not get ground. So if we were to look on the ground sides of things, right now, what's crazy is right here where I just drew that would have 12 volts. Because the 12 volts will go all the way through the bulb, and the 12 volts will be waiting at the point of the open. So that's why the bulb doesn't work. It's got 12 volts on both sides. The second that you close the ground, now like if I picture the cars, right? The second you close the drawbridge, and remember the load is a stalled car, the cars will be like, I'm out of here. But see, these ones behind the stalled car, they'll be stuck. That's where you get your 12 volts behind the load and your 0 volts after the load because the bridge was closed. But if there was an open bridge, those cars would pass the stalled car and be all waiting at the drawbridge, how I visualize it in my mind. All right, so you can see the difference between the two. Positive control on the positive side, negative control on the negative. Technically, we could have eliminated all these if you wanted. Oops. We could have eliminated all those and just done like one switch like this. You could have done one single switch. That would also be ground side controlled. Could be either way. It's not that it necessarily needs to have a bunch of them. It can have just one too. All right. So you guys are going to jump into some worksheets. So let's do it. We'll do a couple examples together. Three examples we're going to do together. Then I'm going to show you a little navigation of a diagram. Then you get to trace your own stuff. All right, let's look at this one. First, you want to do the switch open or closed? We got to do both. All right, switch open to start. All right, if it's switch open, by now we should all be able to identify the loads in the circuit. If we do switch open, we'll start with positive, how we have been. I'll do a trace, a highlight. All right, from the gauge, number 1 goes to here. And then that's it, right? Because the switch is open, which is kind of sad. Which means there's never nothing, so this is going to be ground. All right, so if that's true, what would the available voltage be right here? I agree. What about here? It's green. 0. What about this green one? Oh, I'm sorry. I put it in the wrong line. It should be 0, 0. Okay, nice job. Now, this is going to be a little tricky, but we're going to close the switch. If I close the switch, what should happen? Well, I don't know. Do you want to trace it with the switch closed? Let's trace it with the switch closed. Now the red should go through the switch, right? Because the drawbridge is now down. It's connected. Should go to the splice. Should go to the load. Should stop at the load and not go through the load. So now we should have red going to the load. Now we should have green coming up from the ground and go into the load. It should always change from red to green at the loads. Make sense? That's another way to visualize that. Which means, if that's true, what should I have at this point? What should I have at this point? Oh, that's different. What should I have at this point? Bingo. Right? So when you diagnose the circuit, if you trace it, you pretty much know quickly. If the switch was closed, and let's just say I had a 0 at this point, I should have had a 12 because it's red. If I have a 0, that tells me there's something wrong. Then I might back up to here and be like, oh, that's also 0. Then let's say I back up to here and that's 12. It's between the 12 and the 0, which would be right in here, right? So that's how you track it down each time. Be very similar. So if I were to clear it and you guys wanted to do no tracing, you can. If I were to look at this one with the switch open, what should this have? This is the same. You just don't have the advantage of the colors. What should I have? Switch open. 12. What should I have? Switch open. 0 and 0. Close the switch. 12. See, 12. So you can do this without tracing, right? But it's when you're new, especially, you want to trace and get your thoughts straight. And also, this is a very basic circuit. So on the more complex circuits, sometimes you might want to trace it just to make sure you don't get confused. Because if you're confused and you're thinking that you're supposed to have 0 down here with the switch closed, and you do, you'd be like, it's fine, there's nothing wrong. Be like, whoops, it was actually, I predicted it wrong. It was supposed to have 12, and it didn't, which explains why it doesn't work. All right. Look at this. You've seen this. I'm going to get you some. Yeah, I got you some highlighters and stuff. And also you'll have, I want to know who would like to do this on their devices with their highlighting stuff. Doing this electronically would be a little bit preferred because you can do it one way, save it, delete it, and then do it the other way. Whereas if you draw it with the marker on paper, then I say close the switch, you can't draw it again. You can kind of, so digitally is actually probably a slightly better. All right, this one, we've seen this before. Let's go ahead and we'll do the highlighting like we're supposed to. We agree with this. All right, now switch closed. No, switch open. All right, let's see what should happen. Right, the ground's going to go up to that point, but the ground won't actually make it to the switches themselves. This might trip you out a little bit. Here we go. What do you think about this one up here, switch open? 12, right? What about, let's stay right on here. What about if the switch was closed? Can you imagine? Yeah, it's still 12. Okay, what about over here? Switch open, 12. Switch closed, 12. It doesn't change because the switch is on the ground side. It's the positive side that's not going to change. And this is where it gets a little weird. If this switch is open and we're testing right here, what should it have? What about if we close the switch? It's still 0. See, so, and this one, guess what? This one's going to be the same. So actually, the way that we tested this one didn't really test anything. If you really wanted to tell whether or not those switches are working, we'd have to not test there, but we'd have to actually test like way up in here, like that point and that point and that point, right? Which sometimes can be a little bit hard to do, but you understand. We didn't really test anywhere where the switch would have changed anything. So that was kind of a waste. But that's all right, because it's still true. All right. Now, what about... This one. This one's new. Exactly. And that's what's kind of weird. That one's frustrating because we didn't test anywhere where you could determine whether or not the switch is working. So it's sort of like that was a good one to just get some practice, but not the most effective for actual diagnosis. Which I guess leads to the point. You could take 100 measurements and still not know what's wrong with the car. You got to come up with where to test. So if you understood what I said, the best test points would actually be here, 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 and here. That's what's actually going to test your switches, not where we tested. We did a bunch of tests and it didn't really help anybody. And if I were a customer, I really wouldn't want to pay for that. I'd be like, you didn't test anything. You spent a lot of time, but you didn't get anything done. So I want to pay for what gets done, not just for blind time, digging a hole and then filling the hole back in. Okay, this one's a little special, and this is the first time you've seen it. So, we can see the load in the circuit. There is a stop lamp, a stop and tail for the rear combination lamp right-hand side, and a stop and tail for the rear combination lamp left-hand side. All right, so if we got that, we should be able to do a basic trace. What's the status of the stop lamp switch? You want to start open? All right, if we start open, technically that red would go right up to the point right there. Then what would be on the other side of that bridge? Green. All this is green. Green, green. Everything is very grounded. So with the switch open, what would we have here? Yeah. 12 is right. What would we have here? 0. How about here? 0. How about here? 0. All right. But what if we closed the switch? We close it up. Then we should have 12 volts go through it. Have we hit a load yet? No, so the 12 volts should keep going. Now, I don't know exactly what's going to happen there with that capacitor, but we won't worry about that because that's not going to make our lights not work. Okay, so red, we go here. It would stop there because that's a load, right? It would stop there because that's a load. It would stop there because that's a load, which means on the other side of that load, there should be 0 volts remaining because it's all been consumed. And then these are connected, which means if that's true, we should have at this one with it closed, how much? Yep, 12. We should have closed, 12, yeah, because it's red. In this one, 12. In this one, 0. Right, exactly. You guys are definitely getting there. All right, so good job. Those are the samples. We may do one more sample, but I'd like to show you around the wiring diagram system just a bit. So if I pull, I had a couple things open. The first one is, let's say that you have a vehicle and we're working like on this example. This is a Honda system for the 2024 to 2026 Honda Prologue, which is their EV. let's just say you had headlamps malfunction. You can, so you know, find these diagrams or these step-by-step guides to say like, oh, if the headlamps malfunction, which type of headlamps? Headlamp malfunction, low beam. Ignition and the vehicle off, disconnect the appropriate component, the left and the right headlamp. Verify test lamp illuminates between circuit terminal 1 and B+. If it does not illuminate, repair the open or high resistance, right? Some of the manufacturers realize everyday professional technicians are struggling to look at a diagram and interpret what the measurements should be. This was not the case when I came through. They didn't have guides like this for electrical because if you really know it, you don't need it. So why would they pay people to make guides like this when the real fix is like teach people how to read a wiring diagram and they won't need it, right? So just bear with me. You're going to vehicle off, disconnect both headlamps, verify a test lamp illuminates. If it doesn't, open or repair the open high resistance on the ground circuit or a ground connection. So what we really did was we hooked up the B+ with our test light. That's a known good positive. And then we probed the ground. And if the test light didn't light, it means the ground is not good. That's all it's really saying. So this is giving you the same tests, but it's giving you in a format that's got a lot of words and it's more hand-holdy. So some of this is there. If it does illuminate, that means that the ground is good. Turn it on in service mode. See if it illuminates between B+ and terminal 2. And then we're going to go through and do various steps following these words. I wouldn't count on having access to this, but on some things, it is there. So the way that I would diagnose this would be slightly different. I would pull a wiring diagram. So I'm going to switch over to the Toyota system and show you how I would pull a wiring diagram. And then we can do one in all data just so you know you all have access to this. All right, that one was for fun, Honda. With this one, you guys get to pick. What type of model do you want to do? I don't care. Same to me. No, it's got to be a Toyota.
Yeah, Camry.
All right, so we got a Corolla, a Supra, and a Camry. Well, just for fun, I will show you something, and then you'll understand kind of where I'm coming from. So I will go with an old Supra, but I don't know how old it'll go. So let's go with the Supra Dupra. Okay. Supra. Let's see just see how far back we can go. Let's try, we'll go with a 93. And let's do tail lamps. All right, here's what we've got. Not a ton of stuff. Let me hide this one, move it or something. Okay, we do have EWD, taillight, 93 Supra. Cool. There you go. Let's move this also. All right, if we have that, what I'm going to do is zoom in a bit. I'm going to minimize this so we can maximize what we can see. And here's your basic diagram. So it's there. This is decent. The white one is actually white. The white and lavender is actually white with a little like light blue. L could be light blue too. I don't exactly. Is lavender purple? So maybe L is light blue. Green and white's kind of color coded. You can see this is actually very similar to what I've been training you on because I think some of these older Toyotas are the cleanest and most easy to understand. And if you notice, there's not really all that much going on here. So this would be pretty good. Now, where does white and black go? See this little symbol down there? It's like, where does that go? You probably need to go to the next page. Oh, and look, white and black comes in from here. So now you can trace it, right? So the positive, this is pretty clean, pretty nice. It's got a little bit of color. The negative, you got to go from page 1 to page 2. the reason why in 93 these were like printed service manuals. So you got page 1, page 2, page 3. And page 3's got really good information on the connectors. So if we were to come back to this in the old Supra and say, you wanted to test the light control switch, you see that? Light control switch is component C13. And then let's say you're looking at the connectors and see, in this case, we're concerned about 2 and 11. So remember, C13, terminals 2 and 11. Because let's say that we didn't have any 12 volts coming in on terminal, actually this is mostly ground controlled. Let's say that we're expecting to have ground on 11, and when we turn the headlights on, we should get the ground passed through to terminal 2, right? That's how that switch works. How would we test that? Well, we would probe terminal 11, and then we'd turn the headlights on and we probe terminal 2 to see if ground makes it to terminal 2 or not. If ground makes it to terminal 2, that light control switch is good. But if ground doesn't make it to terminal 2, that light control switch is bad. Get the part price, call the customer, take customer's money. Make sense? But where is terminal 11? Where is terminal 2? Not on this page. Oh, what's this page? Let's see. And also this tells you where the component was. What do we call that component? C13. Take a look at this. Oh, C13. See page 28. Okay, so it might be a little hard to track it down. We could go to terminal. We could flip to page 28 to see where the location is. See that? It doesn't guide you. It's like go to page 28 and then you'll know where it is. So we'd actually have to locate page 28. See, it's old school. All right. However, there's the C13 connector. Do you remember which terminals we were worried about? Look at this. So if you disconnect it, terminal 2 should be right there. So you would make a test at that terminal with your back probe. Test terminal 2, should have ground. Then when you turn the light on, it should pass to 11. Or I might have had that backwards. I actually don't recall. Let's double check.
I'm confused though. How would you see if there was 0 volts at 2 and 0 volts at 11?
All right, so 11 should have ground all the time. See that? Because it goes from ground. When the switch is turned to headlight, that ground should pass from 11 and be linked, see this switch, to 2. So it should be 11 all the time and 2 with it on. So 11, we test and be like, hey, do you have ground? And if there's no ground on 11, you know it would be down on the ground wires. Cool, so if I were to jump back into here, if there was no ground at 11, or let's just say even there's, positive on 11 or something, because that's probably actually how it would be. So I'll take a moment and we'll trace why that would be a problem. But see, it gets a little tougher to trace these when they're full size. So if we had, bear with me on this, if we have 12 volts coming through here, goes to the relay coil, 12 volts would go through this and go to here and go to here and go down here if there was an open circuit right here, you would have 12 volts on 11. You shouldn't have 12 volts on 11. What you should have on 11 would be more like this. Wouldn't you expect to have this turned to ground? Right, so we could trace this and be like, no, this should all be ground. And with the headlight on, we should have ground. So you'd know you should have ground on 11, right? But if you actually go to test it and you find 11 has 12 volts on it, you'd know that you have an open ground down here. That's how you do the diagnosis. The diagnosis is really the same. It's just much more technical when you no longer have a nice, simple, clean diagram and you actually have to get on the car and back probe it. Cool, kind of makes sense? So we should have ground at 11 And if the switch is good and working, we should have ground at 2. How do we do that? We find this connector and we check for 0 volts at 11, and then we check for 0 volts at 2. If we had 0 volts at 11, but we had 12 volts at 2, do you understand what would be wrong? Let's take a look. If we had 12 volts at 2, that would be like this. That would be like, oh, we got 12 volts down here, but then we had ground at 11. I don't think the switch contacts are good, right? We should not, especially if we have it on headlight, ground should travel all up through here. But the fact that I've got 12 volts coming down and ground here, that means that these are not connected, right? Visualize it like a normal switch like this. If you had 12 volts on this side and you had ground on that side, that switch is open. But if you verified you turn it to headlight and you're getting a 12 and a 0, this switch is no good. Sell it to the customer. Kind of see what I'm saying? So it's the same, but it's a little more tricky when you got to track down where the stuff is and where it is and the connector end views, right? So the cool thing is for me, because it's got the little number 2, a lot of times I'll just go right to the connector of this part, the light control switch, and I'll disconnect it and I'll look really closely. And sometimes on the connectors, I can see like a 1 and an 8 and a 9 and a 16. And I'll be like 1 through 8. Okay, so 1, 2, all right, boom, I know 2 will be right there. I won't waste a whole lot of time coming over here because I can pretty much predict it, right? This little dot would be 1. The reason it's a dot is because we're really only looking at the, what were we looking at? The headlights? I forgot what we were looking at. Taillights. So they won't necessarily show you what's in every terminal because they don't have to do with the taillights. Cool. But I could usually figure out where 2 is. And then in addition to it, what color should 2 be? Green. I'll be like, I think this is 2. I'm pretty sure it's 2. And I look and it's green. I'll be like, yeah, it's 2. If I'm not sure, that's when I got to come down to this page and be like, where is 2? Oh, there is 2. Right there it is. Cool. Makes sense? So that's how you get the connector end view and all that type of stuff. And this is a little bit more old school, but that's fine. So that's how we do taillights on an older car. Okay, whether you like it or not, it's what we got. So you could, you're free to hate it if you want. Now,
So it'll have the same like shape with that little thing on the top, so that you can see that number 2.
yes, but the only confusing thing is sometimes this is the front view, so as if you disconnected it and looked at it. But a lot of times, and I'm going to bet you in this case, this is the back side if you left it connected. So that's a very good point, and here's how I would deal with that. Right? It may say somewhere in the service manual, this is a backside view or a front side view. I don't know. One second.
Pablo.
One moment.
Pablo.
Hey, I just saw the time, Marty. Let me jump on in just a second.
Oh no, don't worry. Let me go get the guys. I was upstairs trying to figure out what to do with your 32 computers. That's why I'm a few minutes late. So let me go get the guys. So don't worry.
Please hold. Crap. We were having too much fun, huh? Okay. Minimize. All right, so hear me out on how we do this trick. What if this wire said it was going to be red and this wire said it was going to be black? So if 1 was red and 2 was black, I would reference 2 colors, and then I could look at it and tell if it's the front side or the back side, right? So if it said, I'd look up terminal 1, if it says red and 2 is black, I'd be like, oh yeah, for sure, I got it. This side is 1, and this side would be 2, 3, 4, 5. This side would be 6. But what if it was supposed to be red and black, and I found that this one was like some other random color yellow? I'd be like, oh, I might have the wrong side, and then I might find over here, this one would be black, and this would be yellow. If you were to flip it, you'd be, or it was red. If you were to flip it, you'd know it's the front side, or you'd know it's the back side. So just find the one you think it is, And if they're labeled with numbers, you're good to go. It's really easy. But if they're not labeled, you can reference 2 colors, and then you can see it relatively quick. All right, so I just got one more thing to show you, and then I'm going to print your worksheets and get you so you can take your little break, and then we'll get the party started on that. I think I need to exit this. Give me 1 second. Yeah, so let's say that we pick one new car. We got too excited on this one. I ran over on time. All right, let's go with a 2025. See how amazing this is. And if I do tail lamps and I go EWD, new car features. Oh, it might be too new. Let's see. Let's do a 24. And they may not call it tail lamps either, so I might have to search that. Tail lights. Okay, let's try that. Ooh. All right, I'm gonna have to switch the vehicle up. Let's make it something simpler. Camry. Search. Let's go. Okay, stoplight, tail light. Okay, check this out. And you're gonna be like, you're gonna love this. All right, look at this. It looks a little crazy, huh? All one page. See this? So you don't have to look for where A ends and B begins. You can scroll like this. See how this was never made to be a PDF? This was literally made for you on the computer. Let me X that. All right, so here's the cool thing. Remember how we were looking at that switch? You click right here, and that'll actually pull up this, and then boom, there's your terminal view. And if you want to know what color which one is, it'll tell you. Terminal 4 doesn't have a wire. Terminal 9 doesn't have what. So this must, an unused pin. That's a little surprising, but you can actually look at what every pin is, or if you wanted to know this connector, here's the terminal end view for that connector. So it's pretty nice, and it can even show you what all the different wires are. So I do like the more modern stuff because you can look it up a little quicker. And let's say you wanted to look at, how about here's an LED. If you look at that one, this will even tell you what the number for this connector is and what type of terminals it uses and all sorts of stuff. Makes it really nice for repairing, right? So pretty cool. What wire color it's going to be, everything, right? So this will get you a little spoiled though. When we start doing some of these wire diagrams on all data, you'd be like, oh, it doesn't have any of that, because that's what I was saying. Unfortunately, you can't always get everything, but that one's pretty good. I think you guys we're good. I think you're ready to do the tracing. So we're gonna pause it now. I'm gonna get you the tracing stuff, and then we'll do the trace. And all right. So you can all download this, by the way. So if you're watching video, zoom and download. Let's do this one together. And I'm going to talk you through it. And then what I would do, let's do this. What I would do is do each one of these. And then what I've decided I'm going to do, because everybody's working at a different pace, which is good. I want to make it so it works for everybody. You're going to work on these for a while longer, and if you finish, good. And if you don't and you have to do some as homework, that's okay. Then later or sometime before next week, you can log in and watch this video. So I'm gonna review each one slowly and thoroughly and trace them on screen, but it won't be at the end of class because everybody's finished at a different time. It'll be like something you can look at later today, or I think I'll be able to have the recording up today, but maybe not till tomorrow. Okay. So here's our first one. What type of system are we working on? Can you tell? let me hide floating controls. Backdoor locking with a power window. Okay. All right, so my first question as always is, what the heck is the load in the system? The motor is the load, so that'd be right here. Okay. From there, what's the control device in the system? The switch, yeah. Which would make sense, right? When you guys want to lock and unlock your doors, what do? You press the switch. That's how you control the electricity. And what work is performed? Clunk, 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 right? So now that we got that, we can do a basic trace. However, and this is why I spend so much time explaining, you got to know, like, what are you trying to test? So if I were to start this off with saying the customer states their door locks are in op, how would you verify that? Yeah, press the lock switch. And if you press the lock switch, it doesn't do anything, you're like, oh, your door locks don't work. What would you sell the customer? We don't know yet. Make sense? So this is really how it works. So we'd say, oh, let me press the switch. Do you want to test lock or unlock? It's up to you. You pick one or the other. You guys get to pick it. All right, so if you want to pick lock, we would draw this as lock, which would mean unlock is no longer locked, right? So now that's how the switch is. Now let's test it. So if you were doing this test, you'd have to do it while you're actually pressing the switch. 12 volts should come down, should go here and kind of die right there. And I may actually change this size. Okay, and if it's in the lock position, the red's going to go through here, right? Well, that's a little too small. And that's maybe just slightly too small. All right, so red is going to go through here. Red is going to go through all these connectors. Red is going to go to the motor, but the motor's the load, right? So we would suspect it should most likely change over to ground here. And then where's the ground going to go? Well, it's going to go to here. Look, this switch is still latched here, over, down, across, and to ground. Okay, that is the lock position. Make sense? Here's what's crazy though. Let's say you wanted to change it to unlock. Well, what I really should do is I should close the switch, right? So if you're going to go to unlock, you need to move this over here. And then we need to run, because we moved it, what I'm going to do is I'm just going to run eraser right here. Actually, I'm going to run pen, color white. Right? So see, that's no longer connected. That's an important little detail. Then we go to trace it. This. Red goes down. That's wrong. I'm trying to do highlighter. Red goes down to here, but it also goes over to here, And now look, that's closed, so now it can make it. Wait a minute, is this looking similar? Doesn't that look the same? Oh wait, it's opposite, isn't it? So what's that going to do to the motor? May go the other way. That term, what we just did right there, we did a thing called reversing polarity. If you reverse polarity on a motor, it goes the other direction. So if it was green and red, maybe that would be clockwise. But being that it's red and green, that's counterclockwise, right? So one's lock and one's unlock. Does that make sense? Now, if we were to just apply this to diagnosis, let's say that the car locked, but it didn't unlock. What do you think the problem is? If a car locks, but it doesn't unlock, do you think it's the motor? The motor wouldn't work in one direction, not the other, I agree. Do you think it's this wire? No, because why would it work in one direction, not the other? This wire that's now red, if you recall, was just green. We need that wire for lock and unlock. This wire? No. This ground? No. This positive? No. What's the difference when we lock it and unlock it? There's only one thing we actually change. The switch. So this is what's crazy. If you were super flat rado, if it was, if you're the master technician, if you're the MDT, master diagnostic technician, or if it's Lexus, you're like the, you're the diagnostic specialist, the DS, you could diagnose this car without testing one thing on your meter. If it locks but it doesn't unlock and you look at that diagram and you're like, wait a minute, all the wiring is the same, the motor's the same, the fuse is the same, the only thing that changes is the switch, you could simply analyze this diagram and diagnose it as a bad switch and confidently go get a price on the switch, sell the switch to the customer, it'll fix the car. That's pretty cool, huh? If you really understand it. All right, so that is the walkthrough on that one. That's the only one we're going to do in entirety, but I had a couple people, maybe one or two say they were a little stuck on a relay thing. So I'm going to review each one of these, but I do want to spend just a moment on something with a relay in it. Just in case, I want you to have a good shot at doing this, but also be aware you're allowed to make mistakes, which is why I recommend digital is nice because you can erase it and do it again and do it again. You're going to have access to the video. I'll walk you through every single one. All right, looking at this headlight relay, if we're going to test the headlights, you notice that the loads are over here. How would we test the headlights? What's the first thing that we would do if we were, flat rado technician? Turn on the headlights. Okay, so if I go to turn on the headlights, let's take a look at headlights. See this? Headlights right here. Now when I do that, understand 13 becomes connected and can go down to 11. Okay, that was some of the most important parts. So if now we turn the headlights on, now 13, I know it's tiny to see, 13 is right here. 13 will be connected to 11, which is right here, okay? That's the detail a lot of people miss. Then from there, we change over to highlight. We're going to do red off the battery, red to the relay. Remember, that coil is a load, so we shouldn't go through there, but red does split over here. From there, we could draw it how it really works. We can come up from ground. This is going to do nothing right here. This is going to go to this path. Now this is connected, right? So it's going to go up like this. Don't worry too much about the integration relay. That has more to do with if it's almost like early style computers, because this is an old workbook. This is a 93 Camry. This you'd think would not be relevant, but if you look at the newer diagrams, there's so much going on. It helps to start with the older. Now, if I've got red here and green here, what happens to that magnetic relay coil? It magnetizes, right? Which is going to pull this over. Now this is connected. So if that's connected, now we can go with red coming down, over, up, over, goes here, goes here, goes here, 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 here. And then, this is what's interesting, if we have, let's say you have just the headlights on, you don't have the high beams on. Make sense? You want to be on low. Look, there's no connection here. So what that would mean in the low is, let's see, red, we'd have to go with ground now. Ground is going to go nowhere because it's not connected. Does that make sense? From there, so from over here we do have ground. Let's see where that goes. This light, this light. That's it, which makes sense because look, this is the low beam and this is the low beam, so those are glowing. Get what I'm saying? What if the customer stated they had a problem with the high beams? We would probably have to turn on the high beams, would you say? So if you wanted to turn on the high beams, how do we do that? We would go like this. high beam. That connects 9 to, not to 11, not to 14, but to 12. Cool? And if 9 is connected to 12, now let's see what happens. Now the ground will come up, go over, and go to 12. Now we have ground here, and ground here. And when we have ground at all those points, what is this thing right here that's glowing? That's your little blue high beam indicator. And then, of course, we got additional lights that are glowing now, this and this. We got the high beams and the low beams on. Make sense? So it depends on whether you're in high or low. And I reviewed that a little bit more than I intended to, but I realized maybe that'll help you just do the rest of these, okay? So with that, let's do a pause. And I'm going to have you guys go ahead and do the whole entire packet, and then we'll come back to it.